our body. Similarly, you have taking medicine. Some of the medicines are functional. Most of the because medicine should be functional, it should kill or is a kill your bacteria, kill the virus, and clear in infections. Similarly, there are certain material used in our body which is the body can absorb the material. It does the same function as the part of the body, correct? So that materials are biodegradable and it is absorbable, and also it is a bioactive material that is in the body that we that kind of material used to for generally we call as when you regenerate the tissues, we call the tissue engineering. Treating the regeneration is called regeneration, and the treatment and the regeneration we use a heart tissues. So this slide shows such materials. For example, in the top, if you look at this, you have a tricalcium phosphate, one of the calcium derivative, and the nanofibers of hydroxyapatite and the bioactive glass. These material can be used for osteoblastic activities, stem cells, delivery, stem cells development. Similarly, these milk can be coated on your some of your coat, the material as we discussed in the coating, they can use it on your, but as a filling it can be used. And so it can it can be used. It is also can be used for drug delivery, targeted drug delivery, and all that. It can be also can be used for diagnostic purpose and also for gene delivery and growth factor delivery. It has an n number of functions. Whatever you need, you can do with the material. So that is the recent article in 2015. Mazaharias wrote a beautiful on this materials. So is it new to our body? That's our body. That doesn't mean that our body is made up of his body is complete chemistry. You can see the hydrogen. You can see the our body has a 10% hydrogen, 3% nitrogen, 18% carbon. But because carbohydrate you have, then oxygen is 65%, and there are many other elements in our body, and some of them are you can detect it. Some of them even it is not able to detect. So the trace of elements are there. So you have to use the right material in the right form into the right place. That's very important, right? So in this way, I am taking a material for bone and teeth repair. I just want to show you the two old chart, but it still makes sense. We are using, for example, for a bone, you have a problem with the bone, we are using the material to support our system because heart tissue. But your body shape changes with the time. You put on a very long rod, SS rod inside our body to support your bone. But that your bone shape changes with the time. Your bone property changes with the age. But whereas you are keeping you are still inside. SS or the implant material inside. The implant material is not comfortable with the body is not compatible with the implant. So your revision of surgery is in place. Okay, that means once a revision, a surgery done does not mean that it is lifelong an issue. So, but how often we are doing it and where is the problem? Problem may be due to the osteoporosis, problem due to the hospitalization, problem is due to your different doctors. I mean, they said quite a lot of statistics are being published, and so that shows that the revision of surgery is increasing. So how do we reduce increase of surgery? So can we make a flexible material like our bone? I mean, it should be flexible, or the material, it changes the property with the age, with the time. Also, it is compatible with our body. So there we are looking for some innovative functional material to solve this problem. Similarly, we know that teeth is one of the very important parts in our body, and it is very hot, and that is also made up of calcium phosphate, and your bone is also calcium phosphate. It is not a single material. Both of them are composites. It is not a single entity. So that there is a difference between a mixer and a composite. Composite is a beautiful word, which is different from compound, different from mixture, and different from a lot. Composite is an integration of few materials. It is chemically bonded, and even if you break, and you can see that the material is the original form. For example, the simplest example is the concrete. Concrete is the composite, where you can see gravel, you can see sand, you can see cement, and they are mixing with the water. So the material joined together, they are taking is a complementary to each other. It is very strong, but it is very difficult to break, but it is possible to break. If you break it, still you can see the gravel, still you can see the steel, still you can see the sand. So that means that material is individually it is exists there, but when you combine together, its complementary properties, it is make the material functional, right? So that kind of similarly, our body has a two different composite. One is for bone and another is for then. But calcium phosphate is a basic material, and another element it can be it can be it's an organic material. So the revision of surgery, again we come back to the revision of surgery for in particularly for and the knee and hip. They show up to it is keep on increasing. It says that it will further increase. No, if you look at the 2030, the chart was made in 2005. They are saying that number of the procedure of hip surgery, it's less, but knee surgery the movement is very high. It is increasing. So we have to work on this to reduce these things. But we look at the properties of this biofunctional material. This one is hydroxyapatite, or which is in your bone. This is a bone. When you go to nano level or micro level, you can see fibers. You can see this fibrous structure, and then if you closely, if you go and see the another level, so you can see collagen fiber and see microfibril and bioapatite, which is calcium phosphate, hydroxyapatite, and these materials are exist in the form of nano single crystalline material, and they are function, and the crystal structures are very interesting. Similarly, if you look at your teeth is such a beautiful, it have many layer I'll discuss, and if you see each layer has a different composition and different shapes and different morphology. So these are an actual pictures of bone and teeth. But what is the composition? The composition is the composition of bone is 60% inorganic hydroxyapatite, 20% collagen, and 50% water. But tooth structure is this is 90% it is happy. You can see the enamel, dentin, gingiva, cementum, alveolar bone, but there is a gradient. There is a gradient. So that is a you have to thank the creator. With you have to imagine how the created how many experiments they have done to create such a beautiful structure with the different functions, right? So but here that enamel is the hardest part in our body. It is irrecoverable. Once you lose your enamel, you cannot create the enamel. You can only develop a protecting layer. So there are quite a lot of challenges. This is a recent chart published in 2020 last month, and the material design for bone tissue engineering. Again, it will show you the trend. It will give now actually we are moving towards the biofunctional material, and by using the biofunctional material, we are going for 3D. That is scaffolds and 3D, and expand for more. It can be used for now. It will be further expanded with the innovative ideas. So, in which I am taking the one material for you. What is an hydroxyapatite, which we all know, we have studied. It's a calcium based derivative. We have a very good. It's a crystalline material. 69% of our bone is made up of hydroxyapatite. It is also called biological apatite. And when you put OH, can be replaced to fluoride, chloride, and carbonate, which we call as fluoroapatite and chloroapatite. So when you make this material in nano form, it will improve the osteoblaste adhesion and the cell adhesion, cell differentiation, and proliferation and osteointegration. So but one of the properties, one of the drawbacks of this material is mechanically it is not very strong. It's a synthesized material. So you have to look at the way how you can improve it. This is not new to the industry. It is already being used in microform. And whoever have a ortho problem, you must have used this kind of gels and the blocks, and you have tablets and calcium supplements, right? Used, and where they have this kind of this is also used as a filling material and scaffold and coating material and ligament and rear parts of PCL ligament, and these are the places where we use this. And So what we have done in our lab is we developed a hydroxyapatite material and using very simple approaches, for example, electrospinning, salt gel, co-precipitation, and ultrasonic and very simple methods we used. We improved the mechanical property by using a hard material called alumina. So there, so that we improved not only the biological properties and also mechanical property, mechanical function. Up later, we also developed graphene oxide integrated nanohydroxyapatite for this application in order to increase the osteoblast activity, enhance osteoblast activity. We are, because iron is one of sometimes the lack, sometimes, doctor, you go to, you have to take more iron plate. So there is an iron will, osteoblast activity. One of the functions is osteoblast activity. Similarly, to make a scaffold, we developed this material PMMA and nano have composites. Then recently we developed the sulfur SO4 inhibitor for substitute materials. This is recently published. But however, this material has quite a lot of an issue because of the mechanical property, and in order to improve it, materials are fabricated in nano form, and many people are developing different composition to enhance it. But is there any alternative for this material? Because the another drawback of the hydroxyapatite is only compatible with the hard tissue, not with the soft tissue. When you put this material as an interface material between your implant and your soft tissue, it has a good addition to the hard material. Soft material, it is very difficult to get connection within the, and that's a biological function. So there only Larry Hinch developed this material which is called bioglass, which has basically glass because it is a silica network in which they used sodium oxide, calcium oxide, phosphorus pentoxide, or strontium oxide, and magnesium oxide, iron oxide. They are using different, and they are making a composite. There are two different classes that he has developed. One is osteoproductive, another one is osteoconductive. One is this class A material is a 45% silica. The HCA forms a layer in 7. That means whatever you are using this material, but when you put into this material in your body, there will be a process which is called the biomineralization. That biomineralization changes the material to a synthetic form from to the real form. The real form is HCA layer. It is again the one form of hydroxyapatite layer. So in several hours it occurs. So, but whereas when you use another form of silica, another form of if it is possible, this ratio, another ratio class B. So this class B ratio, it is not compatible. Only it has takes it takes several days to form, and it is bond to soft tissue is not facilitated. So this composition was good. This is a functionality is very good. It can be used for dentistry, it can be used for hemostat application, and it can be used for bone, and it can be used for treatment of cancer. Treatment of cancer, they use in the bone, we call it as an osteosarcoma. They use an hyperthermia process, which we all know. It is you are using temperature, room temperature, 40, and you are you are applying magnetic field to generate the heat inside the body. That will kill the tumor cells, whereas good cell will be preserved because our good cell withstand up to the temperature of 46 degrees, whereas tumor cells will die at 40 degrees. So that when you increase the temperature to 40 degrees inside wherever the place there, your tumor, all your tumor cells will die, but it will not disturb the good cell. This is an alternative treatment for your chemotherapy. It is being developed to implement in all the sites. So these materials are also not new. They have developed many different products and also used for injectable product being developed, but with a different composition, different morphology, or make it more functional. That is our idea. So, and also it has a quite lot of function with the depend on the structure. It can be macro or micro or submicron or nano. But of course, you have a more role to play this in the nano regime. And because it is not only the size changes, it is also the shape very important. crystal structure important, composites important, ratio of the material inside important, individual component is important. That is the reason every material that you use for your research work, try to understand the material down to the level of atom. A single material, a simple material is good enough to understand, to get your PhD if you understand the material well, if you develop the material systematically. So the material what I just take here to teach you, bioglass is a vehicle. When these materials are such a versatile material, it is not only for dentistry, it is not only for orthopedic, it is not only for ophthalmology, also can be used for drug delivery vehicle and wound healing application. So these are the four area. Also you can use this material for various applications as I shown in this chart. It can be used for regenerative material, stop your blood clot, you clot your blood, hemostat, and regeneration and treatment of cancer, and also for as implant coating, and also it can be used for even for water corrosion, water pipes it is being coated. So, but it is already, bioglass is not new. This is a one example. It is used in the Sensodyne paste. We all know that the Sensodyne paste, the advertisement is, when you have a sensitive teeth, you use Sensodyne. There, that is because of your bioactive material, bioglass, that will develop a layer on the enamel that will arrest this one. So, and it can be developed in different form. And it can be bone graft, it can be builder, and it can be bioactive tendon, good and gel. So there are many forms it is used. But now I'm going to show you what we have done for another half an hour too. So we have take this material, we convert it into nano form. But the advantage of the material being in nano is, compared to micro, cell addition is good, specificity is good, cell proliferation is good, differentiation is good, because roughness is very high, biocompatibility is better than micro, osteoblast addition is 24% higher, and also it will simulate the surface topography, which is essential for physiological bones. So this is one. These are the different morphology. This is always any material that we are working in our lab. What we do is we develop the different shapes. One chemistry, many shapes. So we develop spherical, rod, platelet, sheet, branch, dendrimer, cubes, core shell, hexagonal platelet, hexagonal morphology. These are possible shapes that we develop and we studied systematically for the application of these materials. And I show you a few slides on our development. We see, when you use this material for sol gel, first when you develop a sol gel, we have to see the weight loss of this material. So that is, it is around 800 degree. It is the powder before annealing. You can see that up to 700 the weight loss is there. So you can choose the annealing temperature in this region. So when you change the temperature 600, 800, and for a few hours, you can see the variation in the morphology. It is spherical, it can be of rod, it can be of some hexagonal platelet. So that when the changes in the shape and also changes the functionality, see the lysis of the blood from the donor's blood, you can see that your hexagonal plates have very high, others too are hemolysis less. But of course, the control 0.3 is an acceptable region. It is all are well below, but there is a significant difference between these two regions. And then these are the picture shows, this is your blood, and this is a negative the component that we have taken. And add together, you can see the lysis part. All the platelets are lysed down, cells are. So, but similarly, we used for cell line to check the cell proliferation. So we found that our data shows that this material is biocompatible. So it is shows that the temperature variation changes the property but if you based on the morphology and systematic study, you can choose the right material for to make a composite. Similarly, we used different types of annealing to make the material more functional. That is, one is, we look at the hexagonal and spherical and this one. These are when you use a normal annealing temperature and a microwave annealing temperature and use an ultrasonication, that you can reduce a particle size. When you reduce a particle size, surface area increases. surface area increases, porosity increases. That means the other way, porosity increases, surface area increases. Surface area increases, there is a change in the hemocompatibility, and while always it is an alkaline phosphate activities. Certainly, that will enhance the properties of the functionality of the material. We are introducing the porosity by using the probe sonation method that has been developed. That also we recently published in the Biomedical Research Journal. So this is a development on the material. So how do we use in the dentistry? In the dentistry, as I said earlier, so the same picture, you can see the different stacks, and in which each one has a different composition and different function, right? That one, this is one. But we know one of the major issues that dental carries. It is one of the most prevalent and worldwide chronic oral disease. So bacteria causes the damage of the enamel. But it is very difficult to recover the enamel. But you know that enamel has a strontium inside also. So we developed a material by incorporating strontium, and we used it for application. And also we checked with the human teeth. This is from the help of Ramachandra Medical College, Chennai. They check the material to develop a layer on top of the polished tooth. Initially, when you take a teeth and you polish it, you can see all the dentin. The dentin, this is called the dentin tubule. But when you use our material to brush it for 3 minutes every day for 5 days, you can see that the layer grown on top of it. This is the one, and the different strontium content. You can see that the holes are closed. A layer is grown. It is faster than your faster than your pure bioglass. And also it will kill the antibacterial infection. This is clearly shows that this material can be used for tubal occultation application in strontium. It can be used to develop a enamel protection material. So that we published in Journal of Biomaterials in 2008. And then later we also developed some of the product for drug delivery, tissue engineering, and hemostat. So this is another, the same strontium bioglass. Then we taken sodium alginate or gelatin. We come out with we fabricated the gel. From the gel, we fabricated a nano sheets. These are all called scaffold or membranous scaffold or two-dimensional membrane. It can be used for many applications. This is a vehicle. It's a multifunctional vehicle. It can be used for wound dressing. It can be used for drug delivery. It can be for periodontal tissue generation and for various applications. So that is we have developed. And another functional material is, again, we developed this material in colloidal form. Then we used for in the hemostat. Hemostat is, when you have a blood clot with a very high blood is coming out of, when you remove the teeth, you can clot it immediately using this material. That we also checked out with about the thrombin formation, absorption rate, and how it forms. That shows that this material can be used even for hemostat application. That will certainly help. For example, if you have if this is a teeth structure, if you remove the teeth, this will be completely filled with your blood. But if you are not, if there is no teeth or replacement for 1 or 2 weeks, you lose your structure. You lose your extracted sockets undergo resorption and remodeling of the alveolar crust. So in order to do that, if you put a material, here you remove the teeth, your blood is there, you put a material, your scaffold here, right? So that you can preserve the structure, and the material also will regenerate some of the parts, and then by the time you can develop the good teeth, whatever the teeth material, then you can insert it. So you can stop the blood, preserve the structure. That is can be developed. So we developed such a material with the help of doctors. These are the beads that we developed, and these are the hemostat target for 1 person we developed and check it out. And recently we got a project from BIRAC, which is actually, it is an industry sector of the DPT technology, to develop this product, and we with the SRM Dental College. We also studied this material for, cell culture. There are 2 different types of cell culture. One is using only one cell. In every places, our body does not have only one cell. There are more different types of cells. So we also studied the cell additions of epithelial cells and osteoblast cell line and the co-culturing. That is and all we have done. We see that. we have systematically developed this material for next application. And another one is, I think you all heard about, all the advertisement that you are fluoride-rich fluoride-rich paste for your brushes. So they are basically looking for fluorine content. So we incorporated calcium fluoride with the bioglass, but a different concentration. We systematically developed the material and then evaluate the structural properties, and then we look at the biomineralization for different days in our body fluid, that is called simulated body fluid. So that shows that when you vary your fluoride content and the mineralization, biomineralization is faster, the apatite layer is faster. That means it is evidently shown that fluoride enhances the apatite layer formation, regeneration. It is good for treatment as well. That is what we have shown. The erythrocyte compatibility and all the biological coordination and the mechanical improvement in the mechanical properties and biofunctional properties are systematically evaluated for this material and qualified for. This is also already published in Process and Application of Ceramics, and these are the same thing. Sorry. And recently we worked with SRM Dental College, and they took the material and they took a teeth, and then you polish the teeth and they attach this material on the teeth, and then they maintain a certain fluid. We can see that the teeth is growing. This is a sharp when you attach it, but the PG treated, you can see that there is a mineralization occurs on the teeth. So this shows that remineralization of the dentin is possible with the material, and the rate is very fast. So this shows that this is an initial picture. After treated, that you can see that there is a layer grown on top of it. So remineralization can be used. And recently, we also developed a material called the copper bioglass, which we filled for root canal treatment. And this material, and also we qualified, this is a doctor qualified this material, and it is recently we submitted to the Journal of Smart. This shows that the BG sealant is in the tail is the X-ray picture. The penetration of the dye, we check it out, and it is good, and we are improving. And another one is in what we used for orthopedic application. Orthopedic application, again, I just want to show an interesting picture, and for a minute, and we explain. So this is our bone structure. You see my bone, you can see a collagen fibril, and then you further go down, as I said earlier, you can see a hydroxyapatite crystal as well as collagen molecule. These are two components, but there is a one structure similar to our bone in the nature, in the plant, is none other than bamboo. Bamboo has the same structure. It has a cell wall layer, you see, and then if you close it, you have fibril matrix, and then in which you have only two things. This is basically made up of cellulose and another material. So the structure is same. It is recently 2015 they published bioinspired material. It shows that nature has such a beautiful bioinspired material. The structures are used for different applications. Some of the bamboos are very strong, but not all. Some kind of fragile, like our bone only. So, but even if they use when you use an implant material for in the joints, there are quite a lot of failures. The failure is due to this is this implant failure, and there are many reasons. One, it can be your material wear compatibility, or corrosion issue with your body fluid, or then poor integration is not good. Then maybe infection due to your because our body content is different, and the fractures and the surgical procedures also, because doctors are not good, then you have a problem. So, but you look at the probability of the failure mostly due to the infection, and the others comes in later. So only the maximum for the 5 years you have a problem of infection. It is not only due to the implant, it is also due to the change body components. So sometimes we have quite a lot of problems in our body. Become the blood content, the blood quality changes. The food intake will depend upon the food intake or the food quality. Our body has quite a lot of issues that in turn affect the external material that you place in your body. So there you have to improve it. So we have developed such a material which is called a titanium bioglass. It is a coating material using spray pyrolysis. Then we systematically evaluated how it can be used for corrosion. We evaluated this. Developing this material is a very challenge. The material science is a key area because the properties of the material changes with an age, changes with the initial material that you are wearing. We are procuring from different vendor, composition, purity, and your chemistry and your lab and your hands. I mean, when even the person who develop changes, there's a minor variation. Hello.
Yes, sir.
There's some issue, sir. I think there's a disconnected. Is it?
No, we are able to see you, sir. Your screen's also okay, sir, for us.
But microphone is on the whole. I cannot unmute the microphone. Is it? Is it unmute?
Is it? It is audible, sir. We could listen
Okay.
you, sir. Effect of
Okay.
titanium concentration in bioglasses TiO2 nanostructures, and that is the slide which is there as of now, sir.
Right. Yeah. Now, okay. Can you change? Yeah. Next slide. You can see now. Yeah.
Next slide. We are unable to see, sir. You please change, sir. Next slide.
Yeah. I changed it now.
No, we are unable to see, sir. Could you please once again stop and share, sir?
Hanging now. Now it's hanging. Let me share the slides again.
Yeah. Hello, Shiva Garu.
Sir, yes, sir.
Could you please help, sir?
Yes, sir.
Yeah.
Sir, stop. Okay.
Yeah. Is it working now?
Please change the slide, sir.
Yeah. I changed the slide.
We are able to see 60th slide, sir.
Next. I change next.
No, sir. We are influence of zirconia incorporated.
Yeah. That's right.
Only that slide we could see, sir. Now you change slide, sir.
Yeah. Effect of titania, right?
No, sir. It is not changing. Slides are not changing, sir. Shiva Garu, could you please see the things? Yeah, now it is changing, sir.
Now it is changing, sir.
Yeah, I think there is some slow, very slow. Okay, sir. Now do you see the influence of zirconia? Yeah.
Yes, sir.
Yes, sir. Yes,
yeah,
sir.
Okay, then okay, okay. Well, let's go with that. We have So we have used the titania to develop this material. Titanium to improve the functional properties of the material, because titanium is one of the hard component. The material of 1,700, and then when you incorporate, it will form a composite along with that. So biomineralization is good, and the cell cytocompatibility is good. But the percentage is very important, and thickness of the film is very important. That you coat on the stainless steel, that help us to improve the biocompatibility of your steel rod inside your body. This is the one bit that we also incorporated different metal oxides, different hard metal oxide. One is because zirconia and alumina or titanium are relatively strong, mechanically strong. We improved the material mechanical property of the material by incorporating zirconia oxide. So the hardness improved, and anti-feedback was relatively good. And the surface roughness also, its surface is very rough, but very rough means the roughness is uniform, and roughness can be controlled. So that enhances the addition of the cell and reduce the cytocompatibility. So that is also we have studied. So that recently published in Colloidal Surface Interfaces. This is one of the very good material. And the later, as I said, we also developed the material with reduced graphene oxide. And here there are two components that we have changed. In order to change the functionality of the material, we developed a powders, spherical particle as well as nano rods. And then we incorporated with the graphene, we changed it, we get two different types of composite. We evaluated, we found that the bioactivity, antibacterial activity, chemocompatibility, and cell proliferation was good for when you use this material. It's an anisotropic material. That means the nano rods. That with this, it is open a new avenue for biomaterial in the field of implant. So we also systematic this actually this study was done in our IGCA Kalpakam to develop this material, to use this material for hot water piping coatings. And then this another important thing is, from the powder we developed this thin film using EP electrophoretic deposition technique. Then also we evaluated for different staining and positive gram and negative gram. It shows that it is one of the good component. It can be used for, it is scalable to labor to industry, and it's a cost-effective setup. This is recently we filed a patent on this work, and similarly, yeah. So this shows that and again there are another way to improve the mechanical properties. We used in between a titanium platelet and the layer that we are coating, we use titanium dioxide nanotubes that help us to improve the adhesion properties. If you look at this curve, it is a titanium platelet, titanium tube and layer, additional properties, and improve the corrosion resistance. And whereas biochem are equally good, it is also possible to change the hydrophilicity, hydrophobicity of the material. Based on your requirement, you can engineer and you can do this material. So this is one of the another material that we have developed. And here I show you some of the results with the pure titania, and you put an aluminum to titania, and you can see that there is the evaluation to the percentage of calcium on top of the mapping studies and cell proliferations. We have shown the composition. So later we also developed the same EPD technique to also do the bioglass and titania and the EPD platelet, and we systematically evaluated. This is also one of the very good functional material, and we published in Applied Surface Science, I think it's a few years before, but it is one of the work done before graphene. So this is some of the work. And another one is the collagen bioglass. Collagen is a very important material, but what is something new is we extracted the collagen from the fish. Then we developed this collagen material. Then we integrate with your bioglass, because we found that this is a very good biocomposite material, and it is possible to vary your functional properties, addition property, and the mechanical strength and your cell proliferations. That is also, these are both are it comes from the bio sources. The biocompatibility is very high. And as I showed earlier, we have developed a very good nano sheets, but earlier we showed one is gelatin one, and we developed with the material alginate. So there is this called freeze drying and the cross-linking method. And later we also studied let me go. I'll skip this slide because I'm going to show some very other good results. The results. Excuse me because there are too many slides we have, and I'll move to some of the important part. So that is what we have done for coating. Third one is we also developed a 3D porosity matrix. This is a fully integrated geometric structures for large surface to volume ratio to use it for in metro application. So we developed a scaffold. There are bioglass scaffold. This is a PMMA and bioglass scaffold with a different morphology, different porosity we developed. Finally, we achieved very close to the porous structure that where we have. This is our scaffold. This is our actual bone. So this was very simple. You can't imagine this porosity changes in the material just because of the solvent. We use 3 different types of solvent: chloroform, ethylene ethylene plus water, and acetone. If you look at this one, the sizes, the pore sizes changes because of the solvent that we use. You can look at this when you use a chloroform. This is the structure. This is ethanol plus water, then acetone. So you can see that actually we can explain the material formation with the spinodal decomposition. But the property wise, the property wise, if the porosity increases, absorption increases, degradation increases, and then biocompatibility increases. That we have. Similarly, we also developed for putty material, bioglass putty. It can be kind of a sponge. It can be used to fill up any different any metals. And also presently we are working on the the injectable material. These are some of the preliminary work done on our the recent area what they are doing. The last part, another 10 minutes, I'll try to cover the biocompatible work for ophthalmology. This is a joint project from DPT with Shankar Nethralaya Hospital and Chennai. So in generally, in your eye area, you have this material were initially used for develop the bone near the eye. That is with but we found that this material can be used for corneal application. But because when they develop an artificial eye, they are using initially they used to develop the structure of the teeth. They use a titanium platelets and the PMMA. This is your corneal area. But and then in order to reduce the weight and reduce the size, they use bioglass coating or to make it compatible. Then later you completely they are using polymer and biocompatible materials. You can look at this is some of the developmental work. It is reported earlier, and we can skip this one. And I'll go to this Boston keratoporosity development type 1 and type 2, where they use a bioglass here. And but what we have done is we have been working on this material for 10 years, and we have took a new composition. And where you want to have a single phase bioglass, it is 53S. 53S is a name we developed by we developed this material in bar shape and properties we have systematically studied, and we developed a membrane type of structure earlier. This is with the 45S, and later with the 53S bioglass we developed a corneal membrane. The corneal, some of them are one of the property is a transparency. See, this is the transparency is the maximum transparency so far we achieved is 90%. We have to go to very close to 95. And also Shankar Nethralaya found that in their development center, the cell biocompatibility is very good, and also it is they have systematically studied the two different cell lines and showed this material is an ideal material to use it for ophthalmology application. But where and how, that you have to decide. So first of all, if the material is a degradable, you can use it for drug delivery, and also you have to look at this biocompatibility with the tears. That is also we have studied. It is compatible. Second thing, if you develop as a non-biodegradable material, you can use this as a contact lens. So that is what we have. This is a degradation behavior that we have studied, and the property changes with the composition and everything. And now we are developing the second development working on. And if you go to the next stage, what we are doing with the bioglass with the iron oxide, this is a material we developed for hyperthermia application. So if you look at this material, this is actually a pure bioglass with the different iron oxide content. You look at the temperature shows that iron oxide embodied bioglass. It is kind of a core shell shape. We also use this material for cancer drug delivery. Drug delivery is a sustainable delivery, and the magnetic property, yes, it is a highly magnetic. Now this material is ready for hyperthermia application. So if you look at this one, these studies, whatever we presented, the material we systematically developed in different morphology, different composition for different application. It has a very good market. We also did a quick market survey. And what is 2017 and what are the different material used? They used, calcium phosphate, it is increasing day by day. The bioactive glass is a $1 million industry. It's a $1 million industry, and quite a lot of questions that we raised ourselves. No, so as I earlier mentioned, it is not discovering a material was very in 1979, and the clinical application they checked it out. Tissue generation was, as I discussed. Now we are looking for innovative idea. So what I have shown is a different the composition, different functionalities. Now when I want to go for an innovative idea, I have to look at what really we are need. And when I look for a scaffold, what property it requires, where I am going to use it, how compatibility it is. If it is a bone region, if it is a bone region with which bone, the knee bone or hip bone or some other places. So you have to look at all the cell functions over there. Then only you can go for innovation. So that is what we are looking, and we are systematically developing it. And these are our, no, this is not an updated one, but up to 2008, we have a list of all the publications on this material. And this is our group, and new members were joined. And this work started with Dr. Durga Lakshmi, is an MRSI awardee, and my collaborator, Dr. Rajeshri. And those are the students, those who completed PhD under this topic. And recently, 3-4 more students are boarding working on this area. And with this, I also need to thank my collaborators and 3 different projects. This project with Ramchandra Medical College, Dr. Ganesh Venkatram is my collaborator, and Shankar Netra, Dr. Krishna Kumar is and Dr. Soumya is and another new project is with BIOS, is a BIRAC funding. This is HEMA, this is the SRM Dental College. So I have to thank the department. Full support is from DPT, and we have received 3 or 4 projects from DPT and DAE. To this part. With this, I would like to thank our, because I was looking 5 minutes earlier, I can give you more time to discuss on the things. And if you have any clarification, you can discuss. And I'm expecting more questions from you so that I can, whatever I just shared my view, you can discuss with me. With this, I can thank the organizer, and I'll wait for your questions. Thank you, sir. Hello?
Yes, sir.
Sir.
Sir, thank you very much. It was a super fantastic talk and a lot of informative. I request the participants to post the questions in the chat box so that Shainita will ask the questions. Shainita, please go to.
Yes, sir. Today's first question. Will the ceramic implants have resistance to bone infection diseases due to biofilm formation?
Yes, these are this material has a very good antibacterial effect. The first property of the material is look into this one, whether it has an antibacterial effect or not. So that's the first fundamental question. It's a very good question. Yeah, this will have. So you can remove the biofilms. It will avoid the biofilms. Yes. Next question.
No more questions, sir.
No more question. Wow. So they didn't understand, or
they might have understood fully, sir. Thank you. Thank you.
Sir, we have one question. Polymer-based biomaterials, which can replace cartilage.
Which one?
I hope they did not give us a complete question. It has typed as polymer-based biomaterials, which can replace cartilage.
I think the last word is not very clear, but anyway, there are many different kind of material it can be used. But in my topic, I covered only related to the calcium phosphate. There you have a hard tissue. But soft tissues, for example, hard tissues and all, they are using many different types of polymer. PMMA you can use, PLG you can use, our natural polymer, collagen, gelatin, and quite a lot of polymers are available, and it can be qualified also. Nowadays, people are they are designing and synthesizing many different types of polymers.
So we have some more questions.
Yeah.
Is there any biomarker-based studies available regarding tooth analysis?
Yeah, it's available. It's available. If you look at the literature, there are quite a lot of areas, because it's a new avenue working using our biomarkers and the different kind of things. They are using it. They are using it. Yeah, it is available.
Are these biomaterials useful for treating bone fracture fixing?
Yeah, that is what we are qualified this material. Even you have, it can be used in many forms. It can be used as a paste. It can be used as a filling material. It can be used as a hard material. You can also get it with the plasma. Then you can use it for fixing. They are using it, yes, and it can be used even to fix a long cracks as a screws. Yes, correct.
Next question is, which bone implant material is best one till date?
Which one?
Which bone implant material is best one till date?
Best one, last one, what is that?
I repeat the question, sir. Which bone implant material is best one till date?
None other than hydroxyapatite base so far. Actually, there are another material from the day. I think they are asking about the company. So there's a BioAlign. BioAlign is a BioGlass one. BioAlign. Okay. Next question, please.
Is metal oxides can be used as biomarker studies, sir?
Metal oxide is very tough, sir, because they have degradability is not that good. So biomarkers, will easily enter, but they are not, so far it is not being used.
Thank you, sir, for answering all the questions. We are done with the questions.
Sir, are any biomarker based studies available regarding the tooth analysis?
I can share the references. Because recently one of the doctors presented that work. So in my lab, I will share that. It is available. It is available. Yeah.
We are done with the questions, sir.
Thank you, sir. Thank you very much.
Thank you, sir.
Shiva Garu. Shiva?
Yes, sir.
If someone raises a hand, please give a chance to the participants to say vote of thanks kind of thing. If someone raises hands from the participants or feedback. I request participants, one or two participants can give their feedbacks or can talk by introducing themselves. If someone say yes, then you can give a chance to them, Shiva.
Hello, sir.
Yes.
Sir, myself Nagamalli. I'm a research scholar from Andhra University, sir.
Yes, sir.
Just now I have asked a few queries regarding biomarker-based studies and analysis of teeth using nanoparticles and all.
Which one?
Yeah. I want to give a feedback on today's session and last 3 days sessions, if you permit me, sir.
I think your today's session you can give, the past 3 days session you can send it by email.
Yeah, thank you for sharing the information, sir. And teeth analysis and tooth analysis using nanoparticles. Here I'm doing research on breath analysis, exhale breath analysis using biomarkers, sir. Till now I did not explore this tooth and teeth analysis also can be done by using these nanoparticle based studies. In my future works or research projects, I can extend in this particular area. Thank you for your nice presentation and PPT. The topics which you have given are very helpful for future research scholars, sir. Thank you so much, sir.
Thank you very much for your feedback. Thank you.
There are some questions from YouTube also. Let me just check it out, the questions. I don't know how to check that questions actually. Shainita, can you check that YouTube questions?
No, I have asked even from YouTube, sir. I have covered.
Okay then. Okay then. Sir, thank you very much, sir. It was fantastic to be with you and this 1.5 hour. Hello, Balakumar, sir.
Yeah, thank you, sir. Can I leave, sir? Thank you very much for the opportunity given to me, and it's a wonderful session. I really enjoyed the lecture. It's wonderful.
Thank you, sir. Thank you, sir.
to many of the researchers and those who are working in this area, and I have been listening the lecture also. Thank you, sir.
Thank you very much, sir.
Thank
Yeah.
you. Thank you, sir.
Shiva, Mr. Shiva, please make Soumitra Satapathy from IIT Roorkee. Dr. Soumitra Satapathy is available now. Could you please make him presenter?
Yes, sir. Done.
You done?
Yes, sir.
Yeah. Okay, Shainita, could you please introduce Soumitra Satapathy, sir, first to the audience, and then sir will start his talk. Soumitra, sir, good morning.
Good morning. Am I audible?
Yes, sir. You are audible, sir. Your slides not at. Yes, sir. We could see your slides perfectly. Your voice is audible. Just give me 2 minutes to introduce you to the audience, sir. Shainita will do that. Over to Shainita.
Now I'll be introducing our next speaker. Dr. Soumitra Satapathy is currently working as an associate professor of physics and joint professor of nanotechnology in Indian Institute of Technology, Roorkee. He has joined IIT Roorkee in 2014. He has received his PhD and MS in physics and applied physics from the University of Manchester, USA. His areas of interest are experimental condensed matter physics, solar cells, perovskite solar cells, organic solar cells, LEDs, detectors and lasers, memory devices, nanotechnology, nanomaterial synthesis and characterization, nanoparticles and nanofibers, organic nanoelectronic, material science and engineering, sensors, microfluidics, water remediation, drug delivery and imaging, 3D printing, entrepreneurship. In IIT Roorkee, his research group is actively engaged in the fundamental understanding and translational applications of various functional materials using steady state and transient spectroscopy. This includes perovskite-based solar cell, LED, photodetector, etc., and microfluidics-based lab-on-chip device. Dr. Soumitra Satapathy is a TEDx speaker, actively engaged in the scientific development of the society, and the recipient of various national and international awards. He has published 2 book chapters and 47 papers in international journals and 3 patents filed. Now I request Dr. Soumitra Satapathy, sir, to start his talk.
And good to everyone. Thank you, Simon, for the nice introduction. And at the very beginning, I like my gratitude. Thanks to Professor Rao for inviting me to such an exciting STP, which is going on 24th of August. And today, I will be talking about photophysical properties of the perovskite materials and device. Start. I am audible to everyone.
Yes, sir.
Sir. Yes, sir.
Okay, good. So go to the slides. Basically, today we have some internet issues. So I have switched off the video so that you guys can hear me better. In my talk, there will be 3 sections today. In the first, I will talk about the solar energy and what is important in the Indian scenario. In Indian context, we are standing the solar energy research, and then my talk will be dedicated about some basic fundamentals of the solar cell device. And third part of the talk will be more technical, where I will discuss about the perovskites, perovskite-based solar cells, materials, and possible applications. And I will show you some of the recent milestones we have achieved in the lab, and then take the questions if you have. Also, talk if you have some questions, you can always take, or you can put in the chat box. I say that, it is kind of customary to introduce the campus. Always I am coming from.
Satapathy, sir. Soumitra Satapathy, sir.
Yeah.
There is a small blocking part is there in your screen. I don't know, Shiva, could you please help that issue? Just resolve it.
Is it gone?
Yeah, now it is okay.
Yeah. Yes, sir.
Okay. Okay. Sorry for that. Yeah. As I was telling that, I come from this beautiful campus of the North India, IIT Roorkee. It is one of the very green campus in the Himalaya, where you see the river Ganges, Himalaya, and the nature at the same place, and the night view of the campus is also equally beautiful. And one of the figure, this is one of the pictures. Somehow, okay, just give me a minute. Screen has been off for some reason. Okay, I think it is right now. The second.
Yes, sir.
Okay. So this is one of the picture we recently captured near the campus, and as you can see that there is a sunshine in the background. I always say that this beautiful sunshine that inspired us to work on the solar energy. Many of you have read this book by David Goodstein, Out of Gas. If you have not read it, please read it. It's a very, very nice book which discusses about our dependence on energy. As you can all read that from the morning to the evening, each and every activity of ours that depends upon the energy. For example, right now I am giving this talk that is also dependent on electricity, and my talk will be discontinued if there is no electricity is there. The internet connectivity, that also is powered by the electricity. So the whole modern civilization is dependent on the energy. But the fact is that we are mainly dependent upon the natural sources. For example, fossil fuels like natural gas and oils for extracting this energy. But the way the civilization is growing, very soon we will be out of our resources of the existing oil. Then what will happen? So this book is talking about that. And apart from that, there is another warming situation is that which is coming from the global warming. And know that in the global warming, the amount of the carbon dioxide and carbon monoxide emission in our environment, that is equally increasing, and also that is increasing the temperature of the earth. And slowly every day the ice is melting, the rise of the sea level is rising slowly. There is an estimate that the global average sea level is to 2 feet in the next. So it is very dangerous. So in that, many of the continents which exist now will be no longer in the world map. And also at the same time, the aquatic ecosystem will be hampered a lot. And that is going to hamper our lifestyle and our daily life also. It's a high time, think about how to solve this energy problem. Even if I look to the graph, we can see that from the last 40 years, you can see the energy utilizations has been increased almost very, very linearly. For example, from 6,000 milliton to 12,000 milliton, that happened from a time spent between 1971 to 2009. And that increase is not only involved the oil producing countries association, which is called OECD, but also out of those OECD countries, which mainly include the Gulf countries, the demand for this energy is rapidly increasing, which is all been substantiated by the carbon dioxide emission. Once you burn the fossil fuel, you also release carbon dioxide in the environment. As the demand of energy is increasing, carbon dioxide emission is also increasing. For example, from 1971 to 2009, the carbon dioxide emission have increased from 14 GT to 30 GT. And the OECD countries, including India, they have a significant contributions for this increase. This is the present situation in India. So in this slide, what we are showing that what is the projected electricity demand in our country and what is our capacity. That will give you an idea present scenario of the energy crisis in our country. And all this calculation has been made with a basis of a particular GDP. You know very well that this GDP changes from quarter to quarter and like, year to year. And presently, we are probably not doing very good in terms of the GDP growth because of the present epidemic. So these numbers has to be rethought again. So for example, like, if we are considering this area 2021 to 2022, if you consider a GDP growth rate of 7%, then like, the total electricity required in India is 2,397 billion kilowatt hour. Like, or room, like you pay the electricity bill in watt hour or kilowatt hour, but this is billion kilowatt hour. And if you consider GDP growth rate is 8%, then this amount is much higher, 2,866. Whereas the installed capacity in India is only megawatt, that is only 4,80,694, considering a GDP growth of 7%, and 5,74,748, considering a GDP growth of 8%. So that means almost we need a 3-time capacity of generation more than the required present capacity. We have a more demand than what we are currently generating at. And that is like, we have to do the phase electric cut down at different place of the country from the time to time. But as you know, of the sector, especially in industry, semiconductor industry and in medical industry, we can't stop the electricity. So where there is like, 24/7 hours electricity, uninterrupted electricity is required. So it is very, very important that, we can make sure that there is an alternative source of energy is always there. Now, come to Indian scenario. So, where this energy coming from? If you are interested on that, so if you look at this pie chart on the left-hand side, what you will look, the majority of the energy source in India is coming by burning coal, and it almost contributes to 59.8%. Whereas the energy contributes to 14.0%. In many hilly areas, especially in Uttarakhand, Himachal Pradesh, and many of the parts in Jammu and Kashmir, the high energy is one of the major source of electricity productions. Also, the natural gas energy, which contributes to the 8% of our total electricity contribution. There is a parts from the civilian purpose of the nuclear energy that contributes to 1.8%. Diesel consists 0.3% of the total energy production, and the remaining 10% from the renewable energy. Now, what is renewable energy? Now, as the name suggests, renewable energy is something which you can renew it. That means the source is not fixed. You can get it again and again. What are those sources of energy? There are different sources of renewable energy. For example, we have this wind energy. If you go to the coastal area, the energy you can see the time which is generating electricity. In countries, in many places, especially in Netherlands, the wind energy has been used a lot for running the industries. In India, the total contribution of the wind energy to our renewable energy sector is almost 9%. We have the power, biodiesel, so that contributes to 2.6%. And there are small where you artificially generate stream, and then from there you can generate the electricity. And of course, power is there. For example, like, there are different garbage, biomass. From there, you can also generate the power, although the amount is very, very negligible. And the remaining 0.9% is coming from the solar energy. But as you can see that this part is not very large contribution in the pie chart. But on the other side, India, very sunshine country. In most of the part of the India, throughout the year, we get a very good quality of sunshine. So we have a lot of good potential to utilize the solar energy as a source of energy. And this is not specific to any particular place. For example, for getting a very good wind energy, we have to go to the tidal, we have to go to the coastal area, especially where you have a very good wind flow. For biopower, so you have to go to places where there are lots of biomaterials or bio waste has been generated. But solar, whether you come to the northern India or you go to the south India, or whether you go to Gujarat or whether you come to West Bengal, everywhere you will get the sunshine. And there is a potential of generating solar energy. So ultimately, what it means that energy matters. And to be frank enough, energy is the blood of our civilizations. We have the healthcare, we have the problem of the food, but all of this problem run without energy. That's why it is considered as one of the most important rising problem scientists and technologists over the time. And this is a high time we should look about how to generate alternate energy. Because what getting, we thought that this is there for all the time and it will be there for all the time. That is not true. The way we utilize energy very soon, within like 30 to 40 years, all the resources of the carbon fossil fuels will be finished and will be out of any source of energy. So unless until we find out some alternate source of energy, so then it will be really challenging for our civilizations to run. Now, when I talk about the potential of the solar energy in India, I like to draw your attention to this particular pie chart or particular graph, which shows the potential of the different renewable energy in India. For example, like the wind energy, that has a potential of 200 times than the present potential to generate electricity. The bio 20 times potential. That means the opportunity, the work we can do in this particular area. Thermal energy has a times potential. Energy has a times potential. High energy has a 1 times potential. But as you see that the solar energy has a 2,850 times potential than the present capacity. So it surpasses all the other sources of the renewable energy which we presently have. So quite interesting. So then there is a need for putting our concentration and our research efforts to find out how we can generate solar energy. Now, there are lots of government agencies and public sectors, private agencies, they are working on it. And since from my experience of working close with the government sector, in India, there is a very big potential and there is especially a very big research potential in terms of industry also to become energy independent for our country. So today, we'll be talking about the solar energy, how we can generate the solar energy, and how to utilize the solar energy. This is a cartoon where you are showing that the solar panel have been installed on your house, and you can use that solar panel to generate the electricity. As you can see that there is a meter board which have been installed outside and which reads the meter. And if there is any excess power is there, which is not utilized in that particular day, that goes to the grid and store in the grid. And when you need it, it again comes back from the grid and you can use it. So this is the concept of the green energy building. Coming back to the solar in India, so India presently have a potential of 750 gigawatt solar energy. you can see some of the states which are doing very good, including Rajasthan, which is generating 142 gigawatt. And also we are here, Hyderabad, that is also doing very good. The dark gray color, that is the part which is showing, which is contributing to the most of the solar generation in our country. States like Kashmir, Madhya Pradesh, Maharashtra, Gujarat, and others, they also contribute to the estimated potential of our solar energy generation. India get a solar radiation as high as 4.5 to 5.5 kilowatt hour per meter square in most of the region. But to utilize 10% of this. So there is a big potential to utilize the solar energy in India. So now I have talked about that potential, about the solar energy in India, and we are talking, okay, I mean, solar energy will be very good for our country and everything. But what is solar energy actually? So where is it coming from, solar energy? Well, I mean, we all know that solar energy is coming from sun, and it originates from the thermonuclear fusion reaction occurring in the sun. So we know that when the hydrogens, they combine to make a helium, so the mass difference that is converted to the energy according to the Einstein E is equal to mc square formula and generate a severe amount of energy. And that energy by radiation comes to the earth. Now, if you look at the spectrum of the energy, that contains the entire electromagnetic spectrum. So what I mean by the entire electromagnetic spectrum is that it contains visible light, infrared light, ultraviolet light, and also X-rays and some parts of radio wave, where most of the intensity lies in the infrared region. And this radiant energy from our sun is actually the source of life in the earth, and it is there from the millions of years, and it will be there for the millions of years. So there are advantages and disadvantages for utilizing this energy. The first advantage is that it is clean and green source of energy. It does not leave any carbon residue. Well, if I burn the fossil fuel, coal or natural gas, it always emits some kind of carbon byproduct, but it does not leave any carbon byproduct. Radioactive polluting products of the thermonuclear reactions remain behind on the sun while the pure radiant energy reaches the earth. And the energy reaches the earth is incredible. For example, 30 days of sunshine striking the earth, the energy equivalent of the total of all the planet's fossil fuel, both used and unused. Imagine that. The 30 days of sunshine on earth is equivalent to the total amount of the fossil fuel which is stored under the earth's surface. Yeah. Disadvantage, good things comes from some bad things. Sun does not shine in the evening. One person that, okay, we can get the energy in the daytime, but what about the night? Came up with a solution for that also. So we have the battery where we can store the energy and utilize in the night. Second form is that solar energy is a diffuse source. Obviously, in Rajasthan, the intensity of the sunlight and the intensity in Bihar, both will not be equal. And we know that the current produced in a solar cell that depends upon the intensity of the sunlight. So obviously, the amount of the solar energy or power we will be producing in the two different places will be different. But all of those things can be approached and solved by engineering materials and the device. And exactly people are doing right now. Not only generating the electricity, solar energy will be also be good for generating the heat. For example, like this is an ideal house which is made of the wood. If you go to the abroad or many of the winter countries, you will see that the house is made out of the wood. Why? Because wood is insulated. Now, how we can make one of the door or glass window as transparent, and if we can utilize the solar energy as a source of energy, and we can convert that solar energy to the thermal energy, and that thermal energy can be utilized to heat the room. So we don't need a room heater, but it will be acting like a source of room heater in addition than producing for the electricity, provided the room has a very good heat insulation. Not in abroad, India also, in many places, the solar energy has been utilized for generating the thermal energy. And as you can see from the generic diagram, like a flat panel collector is used mainly to absorb the sun energy to heat the water, and this water circulates throughout the closed systems by the currents, and then the tanks of the hot waters are filled, and that has been utilized. To give a practical picture of that, I clicked a photo yesterday from the different parts of the IIT Roorkee hostels where the solar panel have been installed. And you can see that there is a big tank is there, and the solar panels which contains millions of the solar cells. These are silicon based solar cells. Now, solar cells absorb the sunlight, and what convert the solar energy to electric energy. That electric energy heats the water which is stored in the tank, and that hot water is supplied to the hostel for shower and for cooking purpose. LPD stands for the liter per day. So this solar panel can generate 300 liter per day of hot water in his capacity. Similarly, 750, that means that is the amount of the liter per day of the hot water produced from the solar panel, and this has been utilized in one of the laboratories. So whether it is in hostel, laboratory, faculty housing, everywhere this solar panel based heating system has been used in our campus very, very successfully, and in many other places it has been used also. Now come to little science. You have also came across this term photovoltaics as far as the solar energy terms is concerned. Now, this term photovoltaics, it consists of the two words. One is photo, which means light, and voltaic means system that generates the voltage electricity. So a photovoltaic system is a device or a system which converts photo or light to voltage or electricity. If you look at this solar panels consist of lots of small solar cells which have been arranged in parallel array. If we look at the structure of the solar cell, a single solar cell, we see that this solar cell has two parts: boron enriched silicon, and the other side is the phosphorus enriched silicon. The junction between these two parts. In semiconductor physics, we call as a p-type semiconductor, n-type semiconductor. They come across together and they make a p-n junction diode together. So solar is nothing but a p-n junction diode where the n side is heavily doped and p side is lightly doped. We'll come to the physics of the generations of the electricity and voltage later on, and the structure of the solar cell in details. But this is very simple structure of a solar cell. Now, like revolution has been driven by the time, Rome was also not built in a single day, right? So similarly, like solar cell evolution has also went through different stages. 1839, Becquerel first recognized the potential of a photovoltaic effect, and then it went on. The first cell was built by Charles Fritz at 1883. And then there was a revolution happened in the Bell laboratories in US, 1954, where people have found that, especially these three guys, Chaplin, Fuller, and Pearson. So they have found that semiconductor materials can be useful to convert the electricity into the light energies. Going on, this 1958, the human first successful to send a spacecraft in the outer space, where solar panels was utilized to generate the electricity and power the satellite. And one, which I am showing the photo in the next slide. This is the picture of the Vanagat 1, and you might want, like, this is the picture of a satellite which is orbiting around the sun. So this is orbiting around the Earth, and this satellite has two big wings. So why these two big wings? The main body of the satellite is very small, but there are two big wings, blue colored wings on the left hand side and right hand side. These wings are nothing but the solar panels. In the outer space, you don't have any electricity. So who will drive the power of the satellite?
who will drive the power of all the equipments and the instruments inside the satellite? So we have to generate the power, and that's what it does, these solar cells. And of course, these solar cells are not silicon solar cells. These are highly efficient single crystalline gallium arsenide solar cell, which produce an efficiency near about 40%. They're very, very costly. That's why solar missions are so much costly. But if I this solar panel and pick out one particular solar cell, it exists. So it has many parts. As I can view, it has P-type semiconductor and it has an N-type semiconductor, basically a PN junction. And when a P-type semiconductor and N-type semiconductor meet each other, they make metallurgical junction. And all the interesting phenomena happen in this junction. Now, on top of that, we put contact to protect the solar cell from the outer environment. For example, solar panels are installed outside. So there are rains are there are humidity are there. So we have to protect the solar panels from all those environmental barriers. So that's why we put a barrier layer in terms of a cover gas, which has been sticked with an transparent adhesive, white transparent, so that it does not block the light. On top of that, we usually the anti-reflection coating to cut down the reflection. And there is a so basically solar cell is nothing but a sandwich type of structure where I have a PN junction diode sandwich between two metal electrode. One you call it as a cathode, another you call it as an anode. Now, if I bias, which is the work function of the semiconductor material, possible to extract those charge carrier what have been generated in the bulk of the semiconductor, and the electrons and holes can be extracted in this two electrode, and it can run in the outside circuit to generate the electricity. If I do some basic semiconductor physics, I'm sure all of you are very aware of that things. Our theory is that each atom has discrete energy levels. Two electrons with opposite spin occupying a state. Now, when too many of the atoms, let's say I bring 10 to the power 23 atoms together. So what will happen? All the energy levels will split and they form a band. This band in the inorganic semiconductor, we call it as a conduction band, and organic semiconductor, we call it as a lowest unoccupied molecular orbital, or LUMO. In inorganic semiconductor, we call the lowest energy state, which is occupied at T is equal to 0 Kelvin, as a valence band. And in the language of organic semiconductor, for example, plastics, polymers, small molecules, we call it highest occupied molecular orbital, or subtle difference here. The band in semiconductor is now molecular orbital in organic semiconductor. Organic semiconductor, we don't have a concept of the discrete energy band, but rather we have a concept of the molecular orbital, because here now the energy level is overlapped, or the wave function corresponding to the particular atom is overlapping with each other. And when they overlap with each other, atomic energy level, then they make a molecular orbitals. And if the molecular orbitals is filled up by the electron, then it is highest occupied molecular orbital, or HOMO. And if it is not filled up with the electron at all, then it is lowest unoccupied molecular orbital. The scenario you can translate in the language of an inorganic semiconductor by calling the HOMO energy level as the valence band and the LUMO energy level as the conduction band. So usually we know that at room temperature, electron stays at the valence band. But when I shine the light, what happens? Depending upon the band gap of the material, and if we supply enough amount is equivalent or higher than the band energy, electron can make a jump from the valence band to the conduction band, leaving a hole here. Now I have separated the charge carrier. In many inorganic conductor, the electrons and holes, they are very loosely bound. So it is very difficult to separate them. But in organic semiconductor, they are very, very tightly bound. And the result now, right, exciton is a quasi-particle when electrons and holes are bound together. And we have to put more of energy to dissociate or separate the electrons and hole in the case of organic semiconductor. In class 12 physics, we have a conductor, we have a semiconductor, we have an insulator. What is the difference? The difference is the band gap. As you can see, in case of an insulator, you have a huge band gap between the valence band and conduction band, 9 electron volt. A piece of wood, a good example of insulator. Now you come to the extreme side, a conductor. Here, no difference between valence band and conduction band. They are overlying with each other. In principle, there exists no band gap. Fermi level can. Between this extreme, our friend semiconductor is here. Here, the energy level difference is not as high as insulator and not as minimum as conductor, but it is in between them two. So it is somewhere, for example, 1 electron volt. Silicon, germanium, they are very classic example of a semiconductor. So good thing about going around with the semiconductor that these materials are at room temperature, although works like an insulator, generating a very, very small amount of current. But when you apply some kind of external energy, for example, let's say silicon have a band gap of 1.1 electron volt, and if you provide energy more than that, you will be able to separate the charge carriers and you can generate free charge carriers, and semiconductors start behaving as a conductor. And that's why semiconductors like silicon and germanium, they have been used very, very popularly for making solar cells. The very semiconductor which have been used for making solar cell is silicon. Silicon is a group 4 element, and if you on the structure of the electron distribution in the silicon, you will see that silicon has 4 electrons in the valence cells. So that means each silicon can covalently bond with 4 other silicon in its neighboring structure and make a crystalline structure like this. So this silicon, which is sitting at the center, it shares its 1 electron with the neighboring silicon atom, and it shares right side, bottom, below, and up. So now its outer circuit or outer orbit, it has 2 plus 2 plus 2 plus 2 or 8 electron, which is the nearest neighbor inactive structure. So it got a stable structure. So that's silicon actually crystallizes in a very particular fashion. Now, if I want to make a solar cell out of this silicon, now you see that the all electrons are now covalently bonded. So if I want to generate electricity, I have to break this electron. I have to provide the energy, and the energy the solar energy provides, which breaks this bond. And once this bond breaks, so this electron release. And once this electron, the structure becomes destabilized. Stabilize the structure, electron from the neighboring silicon atom jumps here. Again, this silicon already given up its electron, now it has 1 electron less from the stable structure. What it will do? It will now borrow 1 electron from the next nearing neighbor. So this way, the electron will travel to the right hand side, and we can also say that a virtual positive charge or hole is getting displaced on the opposite side. And that's the way we generate the current in the system. I will not spend more time on the semiconductor. We can skip this part. You always know that there are 2 different types of semiconductor. One is called intrinsic semiconductor, which is usually at 0 Kelvin, is an insulator material where there is no impurity. And then the extrinsic semiconductor, which is more interesting to us for making solar cell, where you put some impurity from outside. For example, in the structure of the solar cell, I was telling about an N-type and P-type semiconductor. Now, in an intrinsic semiconductor like silicon, if we put some N-type doping, like any pentavalent atoms, which has an extra electron, so that extra electron will be donated here. So I will have now more number of electrons than the number of holes in the systems. So, for example, in this silicon structure, I put an 1 extra electron by adding some impurity, by adding some impurity. Here the impurity is a pentavalent atom. Pentavalent means which has a valency of 5. So if we add that, for example, like if we add arsenic, have a valency like extra electron here, so that extra electrons comes here. Now if I add energy, this is the valence band and this is the conduction band of the silicon, when the band gap difference is 1.1 electron volt. Now because of this extra electron, or because of this donor atom, an additional energy level has been created just below the conduction band, and that is the donor energy band. And the difference of this donor energy band from the conduction band is 0.05 electron volt. And this amount is very small in comparison to the thermal energy dissociation energy, or the room temperature KT energy, which is 25 milli electron volt. It is very possible by providing some amount of thermal energy, solar energy, to excite those electrons from the donor energy level to the conduction energy level, making the lots of free electrons available in the system. That's exactly we do by doping. Doping, the electron concentration in silicon can goes to 10 to the 16 per centimeter cube. So that electron can generate. In similar way, like if you do a trivalent impurity doping, for example, if you dope a silicon with a boron atom, which actually lacks 1 electron, so what it will do? The boron atom, to get a very, very stable structure, it will grab 1 electron from the silicon. Now, grabbing 1 electron means deficiency electron. Deficiency of negative charge, that's a positive charge. So basically, I am generating a positive charge in the system. So more and more electron taken out by boron, depending upon how much boron you dope, more and more positive charge you generate in the system. So here the positively charged hole are the majority carrier, and that's why they are called p-type doping. And as you again can see, like for example, here in the band diagram, just like the donor energy level, I have created another acceptor energy level, which has an energy difference of 0.05 electron volt, and it is pretty easy to dissociate those energy level so that we can get lots of holes in the systems. Now, these two different extreme ends comes to make a PN junction diode. Then this thing happens. One guy has an excess of electron, another guy has an excess of holes. So at the center there will be a depletion layer. So if I don't, because of the concentration gradient, some electron will flow from this side to this side, some hole will flow from this side to this side. So I will get a current, and that is called minority current or diode current. If current I versus V, I will get a typical diode current, exponential behavior. I is equal to I naught exponential EV by eta KT minus 1. You have all read about this thing, Childs-Langmuir law. Now, what interesting will happen when I apply the bias? For example, if I now add this solar cell with a forward bias junction, what will happen? Forward bias means like, you add the P side of the solar cell to the positive side of the battery and N side of the solar cell to the negative side of the battery. Yeah, I will say negative side of the battery. Then what will happen? Like, so you reduce the depletion layer width. So now more and more electrons now able to inject here, and more holes can be injected here. Right? So now in addition diffusion, you have the drift current. Current has been generated by forward biasing, and exactly opposite thing happens when you do a reverse biasing. Now, in addition to that, if you put the light on the systems, so light energy will also break the electron hole pairs and generating more and more electron in the system. So in addition to the diode current part here, you will have additional part coming from the light, and that's why we call it as a photocurrent. Photocurrent in a solar cell in a PN junction has two parts. One is the diode current, another is the photocurrent. Diode current, that is mainly modulated by the diffusion if it is not biased, and drift and diffusion if it is biased. And in addition to that, you have a contribution from the photocurrent. And the photocurrent, that is proportional to the intensity of the light. I write the photocurrent as R, so that is proportional to the intensity of the light. So if you increase the intensity, then the photocurrent increase, but limit unless until all the bonds breaks down. that case, the characteristics of the solar cell will be modulated. Now, it is important to mention all of you here that it is not for the solar cell. Even if you look at light emitting diode, the heart of a light emitting diode is a PN junction. So if we can understand the PN junction, actually we can understand the solar cell, we can understand the LED, we can understand the diode lasers, the laser pointer, semiconductor laser pointer, which you use for your presentation. That's a diode laser. Photodetector. In our computer, lots of are there. In all the gadgets, there are lots of small silicon photodetector is there. So they are all made of the PN junction. Transistors, millions of transistors is there in an IC circuit. So they are all PN junctions. So PN is the basic device component for many functional electronic device. And if you understand the PN junction, actually 80% of the semiconductor device has been understood. Solar cell, just I have mentioned that when the solar light hits it here, so and now the P and N is together. So now there's band bending is here. There's a band bending has happened, and the Fermi level has been positioned in such a way like to encompass this band bending. And now the electrons start flowing according to the band bending, and hole flows in the opposite direction in this PN junction, and you get a current in the outside circuit. And that's exactly the way a solar cell works. The efficiency of a solar cell. This is a typical IV characteristics of solar cell. And you can see that in the dark, it looks like that. But when you apply the voltage, when you apply the sunlight, so then we have the two part, diode current plus the photocurrent. And that's why we get the JV curve looks like this red graph. And you see that the red graph is now shifted to the fourth quadrant, because only in the fourth quadrant we can extract the power. And this red graph IV characteristic, where it cuts to the axis, that is the maximum current you can get from the solar cell, and that is called short circuit current. And where it cuts the voltage axis, that is the max voltage you can get from the solar cell, and that is the open circuit voltage. Now short circuit current, open circuit voltage. Now you all know that power is equal to voltage. So how much power I am getting from my solar cell? Short circuit current into open circuit voltage. But actually, no, there are different kind of losses in the device. We're all human beings. When we make silicon semiconductor, we can grow a lot of impurity, lot of imperfection in the crystals. Those imperfections or impurity behaves like a trap or defects. And all those defects can grab the electron, and electrons and holes, instead of going to the outside circuit, they can fall in those traps and they can recombine again each other. So that gives to the loss. So all of this loss has to be considered. And also when we make a device, in addition to PN semiconductor, we have also like the metal contact. So there are loss also at that interface at the Schottky junction. So you have to consider loss. So that's why a pure solar cell and a practical solar cell is different. A practical solar cell does not behave like an ideal solar cell. There is a deviation in its performance, and the deviation is written in terms of a quality factor called fill factor, F. Here stands for fill, F is for factor. So fill factor FF. So now in this graph, you can see that, like, you know, I can drop a perpendicular. I can choose a point here in this graph, and I can drop a perpendicular to the current axis, and I can drop a perpendicular to the voltage axis. And let's say this is the perpendicular, like, you know, point which I will get, that is called J maximum power, and this is the perpendicular which I get the maximum voltage. But in reality, we don't get this rectangular shape, but we get a shape like this. So there is a deviations, and this is a very good solar cell. In real solar cell, you sometimes see a very, very bad IV curve also. So this deviation is termed quality factor. That's why the power term, which is the product of the voltage and the current, I have to have a quality factor called fill factor. So the power from the cell is maximum voltage VOC times maximum current JSC times the fill factor. Fill factor is the quality factor. That is the max output. Now, if I divide by the input power, what are the amount of power I am putting inside the solar cell? P output divided by P input will give my efficiency of a solar cell. So efficiency is the product of the open circuit voltage, short circuit current factor divided by the input voltage. And it depends on the band gap. Why? Because the open circuit voltage VOC, that depends upon the band. So voltage comes the splitting the quasi-Fermi level in a semiconductor. So the level, when you make a PN diode in a flat bias, Fermi level does not become a single Fermi level, but depending upon the density of state and the carrier concentration, it now shifted one close to the conduction band and one close to the valence band, and we call them as a level. Difference quasi-Fermi is the open circuit voltage in a device, and that depends upon the band gap. That's why the band gap can impact efficiency. According to the formula, VOC can impact the efficiency. That's why efficiency is impacted by the band. Lower band gap, we have observed higher the efficiency. Higher the band gap, we have observed the lower the efficiency. And like it, I mean, when about the solar cell, you have seen different kinds of solar cell in the market. The solar cell, like see, that is the silicon solar cell. The first solar cell which was made, that was a single junction solar cell. It has only one junction, P type, back contact, front contact, and a glass contact. And these silicons are a crystalline silicon, single crystalline, or even it can be multi-crystalline silicon also. But the efficiency of this silicon cell is very, very high, 31%. Single crystalline silicon, like 16 to 19% efficiency we have got in module, and multi-crystalline silicon solar cell we have got 14 to 15% efficiency. And a theoretical for a single junction cell, which is called thermodynamics limit, which you also know, it comes from the calculation of the thermodynamics if you apply it to a semiconductor, which is called the Shockley-Quasar limit. Maximum efficiency, theoretical efficiency, you got 31%, but we are still less than that. And the cost of the silicon solar cell, single crystalline silicon solar cell, is very high. That's why in most of our practical devices which we use in our home, that's a polycrystalline silicon solar cell. That's not a single crystal silicon solar cell. Now, by doing research, people came the second generation solar cell, which are mainly the thin film solar cell. What are the thin film solar cell? You might have heard about the quantum dot, CDS, CDT, cadmium telluride. People have used this cadmium telluride or cadmium selenide to make a thin absorbing layer, silicon, to absorb the sunlight, utilize it as a light absorbing active material and sandwich that between the two electrode to make a solar cell. Similarly, like the metals, selenium, indium, gallium, so they have also been used to make the solar cell called 6 solar cells. 6 series cell has given you an efficiency of 8 to 11%. Demonstrated efficiency is 80%, and 6 is 7 to 11%, and demonstrated is 20%. So the number is pretty much same with the first generation solar cell. But the good thing is that the cost is less than the production of the single crystal silicon solar cell. And also you have to keep in mind that the application of the single crystal silicon solar cell often involve a very, very high temperature and sophisticated process that actually increase the industrial production cost. Now, why material science research, nanotechnology research is growing more and more. We have new some materials that has led to the third generation solar cells, which you also call as a multi-junction solar cells. There are lots of generation solar cells. They have certain advantages, certain disadvantages. Advantage is there, so make it on any kind of substrate. For example, like if you have seen a solar cell, you have seen that base is very, very rigid. You cannot make it like on a flexible substrate. For example, like you have a college bag or office bag, and if I wanted to paint my solar cell on the office bag or college bag, I cannot put a silicon solar cell. It's a heavy. Or not every house is like the rooftop of the every house is flat. Some people have some design. So how we install silicon solar cell there? Or let's say I have to make kind of smart cloth which will generate and power up my mobile phone during my travel without needing an electricity source. So I have to pay solar panel on my clothes. So then I cannot do silicon solar cell. I need flexible solar cell. flexibility gives this third generation solar cell. Solution processable semiconductor, like the thermal processing, that gives the feasibility of making a printable solar cell. New material, graphite, carbon, all material have been used very successfully for making the solar cell. The future generation of the solar includes the printable cell. For example, you can see the roll-to-roll generation of the solar cell has been happened. And also the organic solar cell, you use the organic materials for converting the sunlight into the power. Some of the organic materials, for example, here we are showing a structure of a material called polythiophene, which is a conducting polymer which can conduct the electricity and generate power. And we have used that for making the solar cell. Our group, we are mainly concerned about a very new types of solar cell called perovskite solar cell. So some parts of the organic solar cells. So lab, like the major focus of the work is our solar cell, where we are mainly working on the perovskite, organic solar cells, and dye-sensitized solar cells. We also work on optical sensors. We work on the also work on microelectronics on the point of care devices. And very recently, we have been started working on the material informatics for predicting the properties of the material by using the machine learning and deep learning. And that was quite successful for predicting the properties of the different material before doing the research. For more details, go to the site of the research lab and you can find out some details. So our major focus, as I said, is that a new types of material called perovskite materials, which have been used in our life successfully for making solar cells, light emitting diodes, for lasing, for making nanocrystal, transistor, detectors, single crystal, all sorts of optical devices, and making gadgets out of it. Now, why perovskites? Like, there are so many materials. There are numeric materials are there are silicon materials are there, like there are quantum dots are there, but why perovskite? So just look at these statistics. Like this is a statistics taken from the National Renewable Energy Laboratory of USA. You can see this, the graph, the y-axis is the reported efficiency and x-axis is the year. The different color shows the different kinds of solar cell. For example, like this blue color graph that is showing gallium arsenide solar cell. So it has started almost 1975. The start point is here, 1975. And until 2010, the efficiency is going like this. You look at pink solar cell, the pink color graph, the efficiency started from almost same time, 1975, and so far until 2018, the efficiency is going like this. But look at the red color graph. It is a perovskite material. It's only 2010 years back, and only 10 years of research, starting from an efficiency somewhat close to 4%. The bottom graph starts from the percent. It is 25% in 10 years of research, and this number is increasing day by day. And you can see the steep of this graph is very steep, that the efficiency is increasing like a revolutionary ways. So that has got the attractions of the people. Although the perovskite was there for a long time, oxide perovskite was there for a long time. It was first discovered in Russia by the Gustav Rose in 1839. And the first person who characterized and observed this material in a great detail is a Russian mineralogist called Lev Perovsky. And according to his name, this material is given the name perovskite. Know where the perovskite came from. Perovskite came from the name of the Russian mineralogist Lev Perovsky. Those materials which have a crystal structure ABX3, they are called perovskite. But the question is so deal about this material. I mean, we have seen that material science, there are lots of wonder materials are there. We have graphene, we have carbon nanotube, we have black silica. I mean, we have so many different materials, smart materials are there. But what is so special about the perovskite? There are some is there. First, not only the efficiency, but this material has a very high absorption coefficient. That means in a very small length, it can absorb lots of photons. For example, you think about the silicon. The silicon solar cell, the thickness of the silicon is in a micron level. So that means you have to make a thick layer of the silicon to absorb sufficient amount of photon so that it is converted to the electric energy and give a reasonable amount of electricity. But the silicon can be done, the similar number of electrons can be generated in a perovskite material only in a width of 500 to 600 nanometer. That is the absorption coefficient. If a material has a high absorption coefficient, then it can absorb lots of light in a very small length. Second, that this material has a ambipolar charge transport property. For example, the same material can work as a p-type, same material can work as an n-type. That's called ambipolar. Third, this material has a good charge carrier mobility. The charge carrier mobility of this material is order of magnitude higher than the other existing material. Very high diffusion length. Diffusion length is the distance electrons and hole can travel before they recombine with each other. So is the diffusion length long? Is good for us. So perovskite, diffusion length is almost about 200 nanometer, and in single crystal they have reported to few microns also. Very good thing. And on top of that, this material is solution processable. You don't need any sophisticated approach, and undergraduate students can also make it in the lab by just doing some simple solution chemistry, and it can be made any surface. Name the surface, you can make the solar cell on it. So it's printable. So the flexibility can be added to this thing, and in addition to that, the efficiency is very high. So because of all these things come inside the same material, high charge carrier mobility, high diffusion length, high absorption coefficient, high efficiency, high values of open circuit voltage. Because of that, the material has got a good traction about the scientific community, and there are still lots of properties are still unexplored about this material, and every day thousands of papers are getting published in this material. Now, if I look at the crystal structure of the perovskite, as I say, the crystal structure has a generic form AMX3, and you look at this figure here, there's a cube here, and inside the cube there is an octahedra is there. Now, if I take one of the and then imagine that all of this octahedra has been surrounded by one octahedra at each corner. I take one of this octahedra, this is one of the corner of the octahedra. I place one more octahedra at this corner. I place one more octahedra at this corner, this corner, this corner, this corner. So I will make a gigantic structure like that, and in the center I will make a void or cavity. So there is an octahedra, and in the center a void or cavity. This void or cavity is with an organic or inorganic cation. Okay, so with an organic or inorganic cation. Now, this octahedra, if I look at the octahedra, so octahedra has like a face, as a corner also. So at the corner head, we put the M, and we have the X halide, which is chlorine iodine, which goes to the face. In general, it is a orthorhombic structure or cubic structure depending upon the symmetry or depending upon the crystal lattice unit parameter. But say hand rule of thumb is that for a material to come across with this structure, there is a factor called tolerance factor that has to be satisfied. And what is the tolerance factor? Tolerance factor, or T, is defined as by these equations. It is the radius of the cation A plus radius of the O. O is the halide here, divided by square root of radius of B plus radius of O. So basically, if I take AX3, where A is a cation, M is a metal, and X is a halide. So if I calculate the radius of the cation A, and if I calculate the radius of the cation B, and if I calculate the radius of the halide, and then if I substitute in this formula, you can do this calculation theoretically by DFT or lot other things, and experimentally by XRD or other things. If you calculate, then you will get a tolerance factor T. For X, the tolerance factor value is between 0.89 to 1. Then perovskite structure is possible, and usually it takes a cubic structure. Oxide perovskite, for example, sodium titanate, calcium titanate, very common used like perovskite oxide, which have been used for ferroelectricity. So the tolerance factor value is between 0.85 and 1. This is 0.89 is for the oxide perovskite, and for the halide perovskite, it is 0.85 to 1.11. So once I make a perovskite, I will also make the lattice parameter calculation. I will first see whether it is satisfying the tolerance factor value. Because if the tolerance factor value is satisfied, then it will give a ABX3 crystal structure. And one can find the structure either by doing some theoretical simulation or by doing lots of different experiments. Direct observation is also possible by today's advent of the microscopy systems. Now here, the very particular class of the perovskite material, which is a hybrid perovskite material, where our this red one or the cation A is an organic cation. Now, if this cation is an inorganic cation, then it will be an inorganic perovskite. If this is an organic cation, then it will be an organic-inorganic hybrid perovskite. So in the time, this organic-inorganic hybrid perovskite, there we use this organic cation Ma, which is called CH3NH3+. This is an organic group. So if we substitute the organic cations, if we substitute the inorganic cesium with an organic cation Ma at the center, we'll get this organic hybrid perovskite. Whereas the things, for example, metal, we use lead, tin, bismuth, antimony, but most commonly and popularly used material is lead. Well, you can that lead is a toxic, and lots of research now going on, like to reduce the toxicity of the materials and how to find out the lead-free perovskite material. But that's a completely different discussion of another subject. So today we will concentrate mostly on the lead-based material. And here the X is the same as halide, chlorine, bromine, iodine. This semiconductor CH3NH3 lead iodide, this is a popularly used organic-inorganic hybrid perovskite in perovskite solar cell, which has given an efficiency near about 25%. It is a direct bandgap semiconductor with a bandgap of 0.55 electron volt, very close to silicon, although a little bit far. And absorption is high, 10 to the 420 per centimeter. And this is the structure. This is the structure of the CH3NH3 lead iodide. Now, the CH3NH3 lead iodide, here the CH3NH3, that is also called Ma. By this perovskite given a name MaPbI3. So from now onwards, we'll call it as a MaPbI3. Now, if we look at the structure of this material, this is a DFT calculation. You can see I was talking about the octahedra, which is like corner shared. And once the octahedra corner shared, then they makes a void, and inside the void there is this organic cation Ma exists. And at that there are halides there, and at the face there is a lead is here. The interesting thing is that if you change these halides, for example, if you replace the chlorine with bromine with iodine, what is happening is that your unit cell diameter or unit cell radius is changing, and that changes the whole structure, that induces the distortion in the structure. Similarly, in this void, we have put right now the Ma. Instead of that, if we put some larger organic cation or some smaller organic cation, that also can induce some kind of rotational distortion in the structure, and that changes the band gap of the material. So for example, if I change it from to bromine to iodine, the unit cell parameter change from 5.68 to 5.92 to 6.27 angstrom, and change the band diagram. Similarly, as I mentioned, this organic cation that introduced the distortion in the network, rotational distortion in the network, and that drives several phase transitions. Now, shows a temperature-dependent phase transition. At room temperature, it shows a tetragonal crystal phase. But at low temperature, if you cool down a perovskite below 160 Kelvin, an orthorhombic crystal phase. And if high temperature, greater than 27 Kelvin, it converts to a more symmetric cubic phase. So it shows a temperature-dependent crystal symmetry. And since the crystal symmetry is different depending upon the temperature, its optical and electronic properties is also changes depending on the temperature. Now, the structure of the perovskites that made by this BX6 octahedra. Here, we have this lead and we have this chlorine. If I basically the lead has this S orbital and halide has this p orbital. So this S and the halide p orbital, they determine conduction band. The S and the p orbitals of the halide, they determine the valence band. So for example, if I look at the electronic structure like here, so you can see that the valence band maxima, that is made by both the lead and the chlorine or bromine or iodine, and conduction band is also made by the lead and the chlorine, bromine and iodine. But in this case of the valence band, the hybrid orbital of the S and the P in the lead, that makes an anti-bonding orbitals, and here they makes a bonding orbitals. So in general, the structure of the perovskite and about some of the basic optical properties of the perovskite. But still, there are some open questions in the field. There are some still very important and open questions in the field. What are those open questions? First of all, once we work in semiconductor, first questions people will ask you, how to get a good morphology, optimum morphology. What do you mean by optimum morphology? We mean I have to have a film where there is as minimum as possible surface roughness is there. As minimum possible non-uniformity is there. Or in other words, the film is very, very uniform. The film has to be very, very uniform roughness and continue with large grain size. That is an optimum film. So how to get an optimum film? I said that perovskite can be easily made by the solution approach. So that is, if we have organic tree, we know that if somebody asks us, okay, let's make a film out of material. Let's take an titanium dioxide. You will dissolve titanium dioxide in some solvent where it goes well. For example, chloroform or PHA or ethanol. And then what you will do, you will make a thin film out of it, either by spin coating technique or by drop casting technique or by doctor bleeding technique. And there are any number of techniques to make a thin film. But the question is, how do you ensure that what you got is a good film? You have to go and take an ACM, and then you have to look at the morphology, and then only you are ensured that you have a good film. If you don't get a good film, then your advisor will go, okay, you again optimize some parameter and again come, and this is not looks good, its cracks is here, non-uniformity is there, not publishable. So then you again go back and then again optimize and again come back, do all those things. The similar happens in perovskite. I have this MAPBI3 as a perovskite material. So if I just dissolve MAPBI in some solvent, for example, DMF, dimethyl formaldehyde, and then if I just spin, I will not get a film. I have optimized a lot of parameters. So the second open is that how to make a large defect-free crystal. In the very beginning, when I was discussing a silicon solar cell, I told that one of the main reasons for the efficiency in a cell is the loss. Loss comes from the defects or traps. Defects at the boundary. These defects can be at the interface. These defects can be at the metal semiconductor interface. Now, when I similarly grow the perovskite crystal, so there can be impurity, imperfection. So the impurity or imperfection gives me the defect or trap. If the energy of trap is low, then we call it as a surface defect states. If the formation energy of the defect state is high, then we call it as a deep defect states. But when surface or deep defect is a defect. So it's a trap for the recombination of electrons and hole. So if the electrons and hole is getting trapped in these defect states, so I don't get lots of current from the circuit. So when I growing the crystal, somehow how I can do the crystal grain engineering to grow a large quality crystal with less grain boundary and less defect. And question which I have already asked before, that lead, and one can argue that although lead is a toxic we use in the battery. Now we commonly use lead battery, although nowadays the lithium battery is getting very, very popular, and in India sodium ion battery is rising. Still, lead is a toxic, but all the people say from the industry that it is more about the solvent which is toxic than the lead. But still, like, considering that lead is a toxic material, we don't want to deal lots with the lead. So there should be some approach, some research should be directed how to replace the lead with some kind of lead-free material and still restore the perovskite structure and still restore the good optical and electrical properties of the perovskite. That's a challenge. And like, how to control the charge transport or photophysical properties in these perovskites. By physical properties, I mean the charge carrier mobility and charge carrier diffusion length. Now, that is an inherent properties of the material. I cannot change it. Whether it's crystalline material, it's a single crystalline materials, or whether it's a nanocrystalline material, depending upon the material, it's fixed. But what I can fix, but what I can try by doing some device engineering and morphology optimization, I can control the charge carrier dynamics. I can control the charge carrier dynamics means I can control those defect states. I can passivate those defect states and I can increase the current. Similarly, I can play around with the material. I can with the additional material, transport materials. I can play around with the interface at the grain to improve this thing, and all of these things will improve the efficiency. Back when the perovskite was first used in a solar cell, the efficiency value was reported 3.8%. 3%, near about 4%. 3.8 is near about 4%. 4 to 5 years, my grad from Switzerland, he said that this material cannot be used as a light absorbing material, but it can be also be useful for a charge transport material. He collaborated with the same transport, and then they did an improved efficiency of 9.8%. For example, like some material can absorb the light, but at the same time, if they can transport the charge carrier also, that is good. So they are doing a dual purpose. Now, after that, lots of people got interested in it. There are lots of research were devoted on this thing by the material scientists and nanotechnologists. And by doing the continuous research, what we can found today, this is called the wonder material of the next century. And we got an efficiency of 25%, and that number is increasing every day. Well, problems still have to be solved before the solar cell comes into the market for commercialization. One big problem, as I said, is the stability. Or the big is the stability of this material. This material is not good. So instability, which comes from from moisture, like this perovskite material, they degrade to their ingredient composition if you expose it to the moisture for a long time. So that can be protected by putting barrier layer. For example, like let's say I put a very highly conductive thin graphene layer on the top. So it's a barrier layer. Or any color of barrier layer, I can put it. So then I can protect the device from humidity exposure. But in addition to that, this big problem of the light induced instability. Now, if you remember, if I go back to my earlier slides, where I have let's go back once earlier slides, talking hybrid perovskite, and I say that hybrid perovskite has this Ma+, which is CH3NH3+. It has halide, which is chlorine, bromine, ion, and lead. So in addition to the electrons and holes, here ions are also present. So in addition to charge carrier by electrons and holes, ion-based charge carrier also takes place here. When light falls on this CH3NH3+, this Ma, this guy has a low activation energy. So it starts moving across the crystal structure. And if this red ball started moving along the crystal structure, then the crystal structure is not stabilized. It disintegrates to the normal lead structure. A phenomena called migration. Big problem in perovskite. And that's the last point, the challenge I mentioned, that the device reproducibility is a big question. But scientists, they have also came across the ways how we can make the reproducible device by minimizing the aggression. But one question which is still unsolved is the stability. If I make a perovskite solar cell that which is giving me 25% efficiency, that is well and good. But what about if the solar cell just die in 10 seconds or 10 minutes, let's say, that will be no useful. So I usually the solar cells are make very controlled environment, in a controlled chamber called glove box, where you can control the oxygen level, where you can control the humidity level, right? But once you try to make outside, then it degrade quickly. So the challenge of the work will be how to develop a stable perovskite solar cell in an ambient condition or room temperature. If we can do that, then we can solve one of the biggest challenge in this field. And that exactly we are doing right now. A method which is called the dual solvent elimination method, which we have developed in the lab. Here what we are doing, we are taking two different solvents. One has a high dielectric constant. Another has a low dielectric constant. For example, diethyl ether is a dielectric constant of 4.33. So here we take the perovskite ingredients of perovskite, which is MaPbI3 and lead iodide. If you mix MaPbI3 and lead iodide, if you put these two guys in the DMF solvent, mix them well, and then spin coat it, and then heat it at 100 degrees centigrade, you will get a black perovskite phase. But there you will, perovskite phase is very unstable. So what we thought, okay, mix the solvent instead of solvent, let's use two solvents. We used a solvent called NMP, which is a dielectric constant of 24.1. So you see the difference of the dielectric constant is not very high. When you same image, the first image is actually belongs to the perovskite film, which has been made in outside the glove box in an ambient condition in Roorkee with the temperature 35 degrees centigrade and humidity is 85%. A very bad thing for solar cell. Nobody will want to make it, but we tried to give a solve. And you see that there's a very bad morphology is there. And if you want to make a solar cell out of it, you will get no efficiency for sure. But when we mix with the solvent NMP, we got a film morphology like this. See that the morphology changes not well. And dielectric constant between these two solvents is also not good. Now, when we went to the opposite, as one of the component of the mixed solvent, we see that the film morphology become much better. The scale, we can see that the grain size become larger, uniform also. Now, what is the reason behind that? The difference in the electric constants means different in the polarity. So the way and the solvent boiling point is also different. When you choose different solvent, which has the same almost near electric constant with a good quality film, when you choose the opposite dielectric constant film, then you get a good quality. What is the reason? Then we played around with a number of solvent, like 60 to 80 different kind of solvent, all solvent available and where it is soluble. Then we have find out that there is a trend that when we have a difference of the dielectric constant in the mixed solvent high, then we can control the nucleation and the crystal growth. So when you have, when the perovskite is solvated in this DMF solvent, so the nucleation starts, but when you put the D there, so what happens? D try to replace the DMF and go and sit in that place. Hamper nucleation. Nucleation becomes, and the crystal growth, and that is a larger size and uniformity. To be curious, we wanted to make solar cell out, and our surprise that this room temperature approach of solar cell give us a reproducible solar cell where the champion solar cell has an efficiency of 6%. That's good. Solar cell without having a glove box by dual solvent method with efficiency of 6%. And the pictures of solar cells which we made in the lab, we make almost 80 to 100 solar cells per day. But what that we have to improve this 6% will not do the job. We have to improve it. So came across with the concept that if you remember, the previous picture for the understanding, let's go back to this previous picture where I was talking about this octahedra. Okay, I mean, this diagram will do, or maybe this will do better. You see that in this cube octahedral geometry, there is a void where this MA cation is there. And I said that the rotation of this MA cation that produces a rotational distortion, and that rotational distortion destabilizes the structure. Now, how it will, like, if we can fill up this void with a large amount of cation. For example, you see that MA is sitting here. Let's say I put another one here, another one here. So then probably I can freeze the rotational dynamics. I can freeze the rotational motion. So those kinds of rotational motion-induced crystal structure vibration that can be inhibited. That exactly took the principle called compositional mapping. So in compositional mapping, what we do, instead of one particular organic cation, MA, we use 3 different organic cation with a particular stoichiometry, and that stoichiometry has been optimized over the years. For example, we use methyl ammonia, we have used formaldehyd ammonia, and we have used cesium also. So organic, inorganic, both organic cation. And instead of iodine, we have used bromine iodine mixture. This process is called compositional mapping. Along with the compositional mapping and the dual solvent elimination method, we are trying to make a solar cell in the very, very large area, 1 centimeter square. 1 centimeter square is considered a large area in perovskite solar cell because most reported is 1 millimeter square. They use this triple cation perovskite solar cell, we achieved an efficiency of 15%. That is stable over 3 months. And triple cation perovskite solar cell by compositional engineering and solvent engineering and in a large area, it was made in a completely room temperature without taking the help of a globe box. Okay. This is some picture of the device which we made. So where we are right now, you see, this is the picture of a globe box in the lab, and this is the iteration we have. And this is another home build setup here, which we made in the lab. This is not a control environment. This is just made over the glass. We said that we will not use the globe box. Globe box is only dedicated for the very, very expert people. So when we made solar cell in the indigenously developed system in the lab at the room temperature, we got an efficiency of the 15% in a 1 centimeter square area, and which is a stability of more than 1,000 hours. If we where in the international scenario, you can see that our efficiency here. We are above the NIMS Japan. We are above the LN at the room temperature stable perovskite solar cell, even at the EPFL. But we still need to we still need to beat IMIT and University of Toronto Sargent's group. But we are doing very here. Go into more physics, like some more fundamental physics. I will not take a lot of time for you because this is more technical details is there. So we are interested to probe, what is the reason behind this? That how triple cation perovskites, how it is minimizing the ion migration in the system. To understand that, what we did a bias dependence impedance spectroscopy, and we also did different kinds of other spectroscopy like noise spectroscopy, transient absorption and transient fluorescence spectroscopy to see the charge carrier dynamics. And what we find out, even in for this high efficiency cell, there is a negative capacitance exists. It's very, very interesting thing. What is capacitance? Negative capacitance is nothing but an inductive element in your LCR circuit. If you draw a equivalent circuit, in an equivalent circuit, an inductive capacitance corresponds to an equivalence, corresponds to an inductive element. So have been repeated that in perovskite solar cell, negative capacitance originates at low frequency only. But what we have observed, it also observed in the high frequency device. That means frequency and stability does not matter, but the negative capacitance is an inherent properties of this material. But this goes out when you put the light. And if you look this region 1 and region 2 and region 3, they are the 3 defined frequency region. One is the low frequency region, another is the intermediate frequency region, another is the high frequency region. So behavior of the capacitance versus frequency graph is different. as you change the bias, from 50 millivolt to 200 millivolt, low frequency, you see that the bias, it is increasing. That is quite expected. These three different regions of the frequency is dominated by three different kind of capacitors. The region 1, the low frequency region, is dominated by the carrier or store capacitance. Region 3, the high frequency region, that's the geometric capacitance, and region is the internal capacitance. So this area is affected by the bias. That means that whatever the charge carrier has been generated in the triple current device, that is still like, in an intermediate frequency or in low frequency, that is still going to the interface. In the intermediate frequency, the increase is quite high, because at low frequency region, like in addition to the electrons and holes, ions are also contributing to the charge carrier, and that's why the ion movements in addition to electrons and hole movements is giving rise to the high value of the capacitance. But at high frequency region, that value is less. So that means even in the triple device, there is some amount of ion migration exists, but not in the high frequency, but only at the low frequency region, and keeping us a room for the development of this device again more. This was the story of a polycrystalline device. If I go to a single crystal perovskite devices, so where you don't expect any grain boundaries, you grow the perovskite single crystal, and we have been able to grow a very large, nice perovskite single crystal of 6 millimeter. Even you can see that this is the iodine, bromine, and chlorine crystals. And what we have, is called like Arbach energy calculations. So Arbach energy is actually calculated at the tail of the absorption spectrum. So whenever we take the absorption spectrum, we usually ignore the longer part, this tail part. But this tail part actually talks a lot about the material. If you can take the absorptions, if you take the wave energy, if you plot for a particular graph, logarithm of absorption and logarithm of energy, you will get a plot like this blue color. And if you take a slope of that, that will give you the Arbach energy. And the Arbach energy of a system represents the disorderness in the system. It is the disorderness in the system. It's another way or novel way of finding the disorderness in the system. Now, in a crystal, you expected to see less disorderness than the polycrystalline material, and that's what we observe. And what you observe that bromine-based material shows more disorderness than chlorine and iodine. Then we are very curious why the bromine single crystal shows more disorderness than chlorine and iodine. To answer that question, we did a temperature dependent ESR spectroscopy. Temperature dependent ESR spectroscopy gives you the land factor. It gives you the dispersion of the landage factor as a function of the magnetic field. From there, we have calculated that the strong spin orbit coupling, what we have found out, that the strong spin orbit coupling in this material actually responsible for this large disorderness in this bromine-based single crystal. And this spin orbit coupling strength was calculated to be very large in comparison to the other similar system, and that matches with the theoretical calculations. Now, important 3D perovskite, that is called the 2D perovskite. Now, I was talking so far about the stability. Now, very recently, what people have found out that there is another way of improving stability. In 3D perovskite structure, if we can introduce an organic group there, so I can make layer structure, and that layered structure is called two-dimensional perovskite structure. Well, don't to be confused with the two-dimensional material like graphene. It's called two-dimensional perovskite system just to find out the difference between the three-dimensional system. In a three-dimensional system, you will have a three-dimensional network, but in a two-dimensional perovskite, you will have a two-dimensional network. And here you got a quantum well-like structure. And this type of structure are called RP structure, according to the name of the two scientists, Rudleston and Popperson. So it is called RP. Similarly, like Depending upon the orientation of the organic group, there are Diane-Jacobs structure is there, and different other kind of perovskite, like structure orientation is there. Now, for example, I have this two inorganic group, and between, if I put an one organic group there, then I call it as N is equal to 1 layer. If I have two between there, the organic group, then we call N is equal to 2 layer. If you have three inorganic group in between the organic group, then N is equal to 3 layer. 4 group, then it is called N is equal to 4 layer. Or if we make a N is equal to 1 perovskite, 2D perovskite, it's a pure 2-dimensional perovskite. So that's like this point things. If I go to N is equal to 2, 3 to 4 to 20, you see there's a color change is happening. And that change shows that the absorption and the photoluminescence properties of this material is changing. We have recorded the absorptions and the photoluminescence properties, and we have seen that that changes from N is equal to 1 to N is equal to 20. But why the 2-dimensional perovskite is more interesting is that because of the organic group here, because of this organic group here, there's a strong quantum confinement effect happens in this 2D perovskite. And that leads to the exciton confinement and large radiative recombination. And that's leads to this 2D perovskite ideal material for making light emitting diode. So far reported a perovskite LED with 20% quantum efficiency of the LED, which is almost comparable to the inorganic LED or the organic material LED. And the good thing is that this multiple quantum well structure, the energy can funnel from N is equal to 1 to 3 is equal to 4. For example, we have a perovskite LED for N is equal to 4 using 2-dimensional perovskite, and we can see a light glow is coming together. These are all kind of LED which you made, and it is quite possible, like to integrate the perovskite solar cell with the LED to have one single device where you can generate the electricity and use that electricity to power LED. So this is a complete package. So this is the beauty of control the photovoltaics in this material system and in this device system. Now, I'm coming towards the close of my talk. Like I will finish this talk with 4 additional slides, and then I will take the questions if you have. So I think I just have to complete this our work, previous work on dye-sensitized solar cells. So I mean, why the dye-sensitized solar cell? Dye-sensitized solar cell is the parent of perovskite solar cell. If you look at a perovskite solar cell, it was first made in a dye-sensitized solar cell geometry. So in a dye-sensitized solar cell, the same, you have a cathode, you have an anode, and you have like a semiconductor called titanium dioxide. And in that titanium dioxide semiconductor, you put some kind of dye or sensitizer. The goal of the dye or the sensitizer is to absorb the sunlight. Okay. The goal of the dye is to absorb the sunlight and generate electrons and holes. Then electrons will go to titanium dioxide, and then it will go to the FTO, and the hole will go to the platinum counter electrodes. And to regenerate this process, we have to use some iodine triiodide redox electrolyte. So this is the structure of a dye-sensitized solar cell. Very simple, even a class 12 student can make it. You take an ITO conductive glass substrate or FTO conductive glass substrate. You take titanium dioxide. You make a very thick layer of titanium dioxide, and then you put any kind of dye in here. Soak the titanium dioxide in dye, and then leave it overnight, and put a counter electrode like platinum, and then sandwich it using some kind of clip or something. And then you measure the current and voltage using a multimeter, and well, you will get a very measurable amount of current and voltage. And if you are lucky enough, you will be able to put a light, small LED light on also. Now, what we did, replace the conventional these dyes or sensitizers with a common fruits which you eat every day. You all heard about the jamun fruits, right? Jamun, doctors say that you eat it regularly for your health. It has a good antioxidant, anti-cancer, anti-inflammatory properties because it is rich with a lot of antioxidants. So, but thanks to our mouth that if you look at the jamun fruit, I have given a picture of the jamun here. So it looks dark. It gives this dark color. So it has been seen that in the history of science that anything dark color is good for the dye. That has been used in the dye industry also a lot. So we were curious, like, okay, so I mean, can we use this, this jamun for making a solar cells? So we just use the jamun extract, just put it in an ethanol extract. You put the jamun, we pluck the jamun from IIT here. We have a lot of jamun trees in the campus. Pluck it and put it in the, ethanol, and then get the extract and then make a solar cell out of it. Our imagination, we got an efficiency of 0.5. That's good thing we did not do that. So they continue our thought by extracting some impurities. We have been able to improve the efficiency of 1%. This is one of the pictures of our Jamun solar cell in the lab. And this is popularly called Jamun solar cell. And of you have read that in 2016, it was in almost in all national and international news, and it was the second highest read article in the Hindu. And there is a TEDx talk also given by me. If you are interested, you can go to the YouTube and can listen to the talk where the working principle of this solar cell has been talked in details. Last but not the least, I just we have societal responsibilities so that, and as you know that we are living now in a very, very challenging time, and that's why we have this workshop online. Otherwise, I should be in Hyderabad right now giving the physical presentation. But nowadays, because of the COVID, everything has been changed. So because of the continuous hard efforts by the students in the lab, was able to work for the societal innovations, and some of the innovations has been greatly appreciated by the Ministry of Human Resource. And you can go to the MHRD website and you can see some done by our lab. And based of our initiative, we have made this Biofluidics Innovation Private Limited, a complete students initiative, and showcase the two product or device which might be useful for all of you in this present situation. One thing, we have made the COVID-19 screening booth, which is a very lightweight, portable, contactless screening booth for swab sample collection. And here we use the UVC light, and it's highly affordable in Indian market. So we have given almost 20 to 30 of that things to the city, and they have been used in the Haridwar, Dehradun, extensively in Uttarakhand, and also in some places in Delhi also. But the second thing which students came across that is a chamber. It's called the Unisevere disinfection box. This is a chamber where optics, electronics, artificial intelligence come together, which have been developed for sterilizing the personal belongings. Like many times we go to the market and after coming back, sanitize our personal belongings like mobile phones, even our clothes, fruits, PPE kits, jewelries, etc. So it is not possible to put the sanitizer on everything. So that's the idea. We made this box. There is a tray in between. One can put all the gadgets here, mask, PPE kits, jewelries, and everything here. There is a unique geometry. There are some standardized UVC light on the top and the bottom, and we have to calibrate the power according to the international standard, how much you need from the sterilization of the different thing. Then at the center, we put a antiviral and an antibacterial coating made by the herbal products, and that have been approved by the National Institute of Virology, Pune. And this has been patented technology. And to make it a kids safety things, and also for the people can use it very, very safely, we put a artificial intelligence coded a timer. So that means if there is a screen outside, if you just write I have put my clothes, there is an option clothes. So the instrument will smart enough to understand that now it has to monitor its UVC light intensity so that it is for the clothes. If you want to fruits, you don't need a lot of intensity. So then you can monitor according to that. So that is a perfect example where the nanotechnology, material science, and everything should come across together. And right now the plan is that to self-power it by using a solar cells. And I think that is the essence of this STP conference together. But last and not least is that I actually, this is all credit goes to all of my students. This is a small subgroup of students. We have almost 20 people in the group. This is a solar group. Who are present in one of the operations. And I also thank the DST, MLRE, and Ministry of Information Technology for their gracious financial support. And and finally, thank you all for your patience and hearing me such a long time, 1.5 hours. And thank you all. And I'd like to have any questions if you have.
Thank you very much, sir. It was a fantastic talk. We did not even felt that it is a 1.5 hour time. It went on very, very smoothly and very interestingly. Lot of aspects were discussed here. Thank you. Over to Shainita for the chat box questions and YouTube questions, please.
Yes, sir. My first question today is, what's the status of the lead-free perovskite solar cells efficiency till date? Are they comparable to lead-based perovskite solar cells by parameter of efficiency?
So is the question is what is the status of the lead-free solar cell or lead-based solar cell?
It is lead-based perovskite solar cells by parameter of efficiency.
Okay. Good. Yeah. It's a good question actually. As I mentioned that the today's date, the efficiency in the lab reported efficiency of the perovskite is 25%. Okay. There are challenges to overcome to bring it to the market in a panel form. For example, like if you look at a single crystalline silicon solar cell, the efficiency is near about 20%. But once you make module, the efficiency is 15%. So there are some companies like not in India. For example, like there is a company in UK called Oxford Photovoltaics. You can Google it. It has been established by an Oxford scientist called Henry Smith. So they claim to bring by the end of this year a perovskite silicon tandem solar cell panel efficiency 28%. Similarly, like there is a big consortium of the European Union called IMET. So they also claim to bring by next year a perovskite module of an efficiency near about like 20%. But still today's date, if you me that if the perovskite panel has been installed, yes, there are only two places. One is in Japan, and the module efficiency of 15, and Switzerland, that is 15%, the same company. But a lot of things to be optimized and improved to material from the lab to the practical real day.
Okay. Thank you, sir. My next question is, can we use the fabricated perovskite solar cells for underwater solar cells applications?
Yeah, actually, that's a very interesting question. Like in submarine and all the defense technology, this is a big question, right? So if that's as I mentioned that solar cell, the perovskite solar cell is not very stable with the moisture and water. So what happens, like this CH3NH3 lead iodide, once it come in contact with the water, so it makes a complex called CH3NH3 lead iodide 7H2O. Then that complex is very unstable, and then it disintegrates to lead iodide and component CH3NH3+. So the perovskite crystal structure gets lost. But thanks to the different barrier technologies improvement, for example, by putting a thin insulating layer of the PMMA or a thin layer of the graphene or the different kind of polymers layers, it is now possible. And also by utilizing the ALD, atomic layer depositions, people have been able to develop a perovskite solar cell, and there are lots of papers are also there where they show that if they dip the perovskite solar cell inside the water for 5 to 6 hours, the efficiency does not change. So that is something optimistic. So I think once the barrier or the insulation technologies so that the solar cell can be protected from the water and the humidity level, that has been optimized, then it's not a very big problem like to make the solar cell, to bring the solar cell inside the water. That is one aspect. But the second aspect is that if you go inside the water, your sunlight, you are also getting compromised there. You are not getting a lot of sunlight. You are getting a very diffuse light. Okay. So that is the question. Like in that case, the perovskite solar cell alone cannot work. So you have to use a concentrated CVV, concentrated solar cell along with the perovskite solar cell to harness the power in that case. But that's I will see at this state a kind of like a very dream project.
Can you give some more information about the conductivity of Jamun precursor used in the solar cell?
Please, once again, your voice was breaking. Conductivity of.
Can you discuss some more information regarding the conductivity of the Jamun precursor which was used in the solar cell?
Okay. So you see that mentioned that this jamun, like they contain this anthocyanin. Now, anthocyanin comes with 100 different isomers, and it is extremely difficult. I will say it's impossible to extract all the 100 different anthocyanins, but to get a perfect, anthocyanin which will contribute to the good absorptions and the good conductivity. So in many often we get a mixture of the anthocyanins. Okay, and if we are able to extract the this pure anthocyanin, and usually it is done by the HPLC techniques, so then it is possible, but that is not possible because the molecular weight of them are so similar. It is not possible to separate them a individual anthocyanin and to measure their conductivity. So what we measure is actually the conductivity of the mixed anthocyanin, and this mixed organic compounds conductivity is if you compare to the normal organic semiconductor, it is comparable to the normal organic semiconductor, but not as high as the inorganic semiconductor. Okay.
Does polymer nanocomposite has some scope in energy conservation or transformation process?
Oh yeah, I mean that is nano have a great potential. For the energy conversion and storage process also. I have not discussed there is a completely different domain that is called organic photovoltaics. So there are bulk heterojunction solar cells and organic nanocrystal solar cells is there, where the these polymer nanocomposites and the polymer have been utilized a lot. For example, people have been used this polythiophene P3HT and small molecule PCBM for making these polymer solar cells. And they also came across with a different kind of polymer, copolymer and block copolymer, polymer nanocomposites for optimizing and developing the solar cells. So there is a great potential, and there are a lot of people are working in that area.
Thank you for answering all the questions, sir. We are done with the questions.
Okay.
Thank you very much, sir. It was a fantastic talk. And all the people are giving feedback, sir. Once the feedback comes, I will give you once again. I will send you the report, sir. Thank you, sir. Thank you very much, sir. And for today, we will signing off. And tomorrow by 9:40, we will gather once again. Very good day to you all, and happy to see you all here once again tomorrow. Hoping you to see very actively, but tomorrow. Shainita, anything need to be announced?
No, sir. As of now,
okay then.
Okay, Venkateshwar sir, we are closing the session.
Kivaga, you can close the session. Thank you.
Okay.